Somewhere out there, beyond the edge of what any telescope has ever captured in a single frame, something exists that makes our understanding of size feel almost quaint. We have measured the largest galaxies. We have cataloged their dimensions and marveled at spans of millions of light years. But what if those measurements, impressive as they seem, represent only the beginning of a much larger story? The universe has a way of humbling us. Every time we believe we have found the biggest thing, a new discovery arrives and gently reminds us that our sense of scale needs adjustment. This has happened before. It will happen again. And the discovery we are about to explore does precisely that, but in a way that few people outside of specialized research circles have fully appreciated. When astronomers talk about the biggest galaxy, they typically mean a single island of stars, perhaps stretched by radio emissions or bloated by countless mergers over billions of years. These objects are genuinely enormous. Some span distances that would take light millions of years to cross. Standing beside them, our own galaxy would appear modest, a small spiral lost in the shadow of titans. But here is something worth considering. What if the very concept of a biggest galaxy misses the point entirely? What if galaxies themselves, even the most gigantic ones ever detected, are merely small components of something far more vast? Not just larger in degree, but larger in kind. This is the shift in perspective that recent discoveries have made possible. And once you understand it, the universe begins to look different. The biggest galaxy stops being the ultimate measure of cosmic size. It becomes instead a single brick in a wall that stretches beyond imagination. To understand why this matters, we need to step back and consider how the universe organizes itself at the grandest scales, not at the level of stars or even galaxies, but at the level of structures so immense that galaxies within them appear as grains of sand scattered along invisible threads. This is the realm of the cosmic web, and it is here that our sense of what counts as truly big must be rebuilt from the ground up. Picture a single galaxy floating in space. It contains billions of stars, clouds of gas, wandering planets, and at its center, perhaps a supermassive black hole. This is already a structure of staggering complexity. The distances involved dwarf anything in our daily experience. Light itself, the fastest thing in existence, takes tens of thousands of years just to cross from one side to the other in a typical spiral galaxy. Now imagine grouping several such galaxies together, not randomly scattered, but bound by gravity into a cluster. These galaxy clusters can contain hundreds or even thousands of individual galaxies, all orbiting their common center of mass. The space between these galaxies is filled with hot gas and dark matter. The whole assembly might span several million light years. This is already larger than any single galaxy. A galaxy cluster contains many galaxies, obviously, so it must be bigger. But clusters themselves are not the end of the hierarchy. Zoom out further. Galaxy clusters are not distributed evenly through space. They tend to gather along certain paths, forming elongated chains and dense knots at intersections. These are the filaments and nodes of the cosmic web. The filaments can stretch for hundreds of millions of light years, connecting massive cluster junctions like a network of cosmic highways. And still, we have not reached the largest structures. Beyond filaments lie superclusters, which are collections of clusters and the filaments connecting them. These superclusters can span hundreds of millions of light years containing the mass of quadrillions of stars. But even superclusters are not the final level. The largest coherent structures we have identified are often called great walls or great attractors, depending on their properties. These are assemblages of superclusters, and the filaments threading between them, stretching across billions of light years. This is where the discovery we are exploring comes into focus. Because when scientists identified structures at these scales, they found something that makes even the most enormous individual galaxy seem almost negligible. Not because that galaxy shrank, but because our frame of reference expanded beyond what anyone previously thought possible. Let me offer an analogy. Imagine standing on a beach and being told that a particular grain of sand is the largest grain on that beach. You might find this interesting. You might even examine it closely, measuring its dimensions and comparing it to neighboring grains. But then someone taps you on the shoulder and points toward the horizon, where you notice for the first time that the beach itself extends further than you can see, curving around a continent. The grain is still large by grain standards, but the beach and the continent it borders exists on a scale that makes comparing grains feel like a different category of question entirely. This is what happened with our understanding of cosmic structures. The biggest galaxies are impressive, but the cosmic web reveals that galaxies are simply the places where matter has concentrated most densely along threads of a much larger tapestry. The discovery that prompted this reconsideration did not arrive with dramatic fanfare. Like many of the most important findings in science, it emerged gradually from careful observations and painstaking analysis. Multiple research teams, using different instruments and techniques, began noticing patterns that did not fit previous models. These patterns suggested that the large-scale structure of the universe was even more organized and extensive than earlier surveys had indicated. Regions that appeared to be separate clusters were actually connected by bridges of matter, too faint to see directly but detectable through gravitational effects. What looked like empty voids were not truly empty, but contained sparse populations of galaxies arranged along nearly invisible threads. As the data accumulated, a picture began to form. The universe was not just sprinkled with galaxies and clusters. It was woven together by a network of matter that stretched across observable space, forming walls and filaments and nodes in a pattern that some have compared to a three-dimensional spiderweb. And within this web, certain structures stood out as particularly massive. These were the Great Walls, sometimes spanning billions of light years from end to end. To put this in perspective, a billion light years is roughly 10,000 times the diameter of the largest known individual galaxy. The scale difference is so extreme that comparing them directly feels almost meaningless. Yet these structures are real. They have been mapped, their properties have been measured, and their existence forces us to reconsider what we mean when we talk about the biggest things in the universe. Consider this. When light travels from one end of a great wall to the other, it has been traveling for billions of years. During that time, stars have been born and died. Galaxies have collided and merged. Entire solar systems have formed, evolved, and been destroyed. And still the light has not completed its journey across this single structure. The biggest galaxy, by comparison, might take light perhaps 16 or 20 million years to cross at most. That sounds like a long time, and it is by human standards. But compared to a structure requiring billions of years for light to traverse, even the largest galaxy appears as a small feature within a much grander architecture. This is the discovery that reframes everything, not a single object bigger than all others, but an understanding that the category of objects we were comparing was never the most meaningful measure of cosmic size. Galaxies are nodes in a web. The web itself is the structure that defines the shape of the universe. But let us not rush past this too quickly. The implications deserve to be explored with care. First, what exactly is the cosmic web made of? The answer involves both visible matter and something far more mysterious. The visible part consists of galaxies and the gas between them. When we look at the cosmic web through powerful telescopes, we see the galaxies most clearly. They light up the nodes and trace the filaments, like light strung along invisible wires. The gas between galaxies is harder to detect because it emits very little light, but it can be observed through its effects on the radiation passing through it. The invisible part is dark matter. This substance, whatever it is, does not emit or absorb light. It does not interact with ordinary matter except through gravity. Yet it outweighs visible matter by roughly 5 to 1. When astronomers map the cosmic web, they find that dark matter forms the scaffolding on which ordinary matter collects. The filaments of the web are primarily dark matter filaments, with galaxies forming along them where conditions allow. This means that the structures we see are actually just the visible traces of a much larger dark matter framework. The true cosmic web is mostly invisible. What we observe directly represents only a fraction of what exists. Understanding this changes how we think about the biggest structures. A great wall that appears to span 1 billion light years of visible galaxies is actually embedded within an even larger dark matter structure. The gravitational influence of this dark matter extends beyond the visible boundaries, shaping the motion of galaxies even outside the apparent limits of the wall. In a sense, the visible universe is like the frost on a window. The frost shows a pattern, but the pattern is determined by the glass beneath, which you cannot see directly. The glass shapes the frost, just as dark matter shapes the distribution of galaxies. This is why the discovery of the cosmic web's true extent was so significant. It revealed that what we thought were the largest structures were actually just the illuminated portions of something even more vast. Let me describe one of these structures in more detail to give a sense of the scales involved. In a region of space visible from Earth in the direction of a particular constellation, astronomers have identified a concentration of matter that extends across an almost incomprehensible distance. This structure contains thousands of galaxies arranged along filaments that converge at dense knots. The whole assembly stretches for billions of light years. To visualize this, imagine taking every galaxy within this structure and replacing it with a single point of light. Now connect those points along the paths where matter flows between them. You would see a network resembling the neurons in a brain or the strands of a cobweb. Some regions would be densely packed with connections. Others would be sparse, nearly empty, with only thin threads crossing the void. The dense regions correspond to galaxy clusters. The threads correspond to filaments, and the empty regions correspond to cosmic voids, vast bubbles of space where almost nothing exists. Now consider that this entire network, this brain-like pattern of galaxies and connections, is just one structure among many. The observable universe contains numerous such assemblies, each with its own filaments and voids and clusters. Together, they form the cosmic web that fills all of observable space. When we speak of the biggest galaxy, we are identifying one bright point within this network. That point might be larger or brighter than its neighbors, but the network itself operates on a scale that transcends individual galaxies entirely. This is the perspective shift that the discovery enables. The biggest galaxy is still noteworthy, but it is noteworthy in the way that a particularly large city is noteworthy on a map of the entire world. The city matters, but the continents and oceans that contain it matter in a different way and at a different scale. The research that revealed these structures involved multiple approaches. Optical telescopes mapped the positions of millions of galaxies. Radio telescopes detected the faint emissions from intergalactic gas. X-ray satellites observed the hot plasma-filling galaxy clusters. And gravitational lensing surveys traced the invisible dark matter by measuring how it bends light from distant sources. Each method contributed pieces to the puzzle. Alone, any single technique would have provided an incomplete picture. Together, they revealed a universe far more structured than earlier generations of astronomers had imagined. One of the key insights from this research concerns how these structures formed. The cosmic web did not appear suddenly. It grew over billions of years, shaped by the competing influences of gravity and cosmic expansion. In the early universe, matter was distributed almost uniformly. Small variations existed, tiny differences in density from one region to another. These variations, though minuscule, were enough to seed the growth of structure. Where matter was slightly denser, gravity pulled in more matter from surrounding regions. This made the dense regions even denser, attracting still more material. Over time, these regions grew into the nodes and filaments we observe today. Meanwhile, regions that started with slightly less matter lost material to their denser neighbors. These became the cosmic voids, growing emptier as matter flowed away toward the filaments and clusters. This process took billions of years. The cosmic web emerged gradually, like a photograph developing in slow motion. The largest structures formed most recently because they required the most time to assemble from smaller components. This growth continues today. Matter still flows along filaments toward clusters. Galaxies still fall into their gravitational wells. The cosmic web is not static. It is a dynamic, evolving structure that will continue changing for billions of years to come. Understanding this growth helps explain why the largest structures are so much bigger than the largest galaxies. Galaxies form relatively quickly, on timescales of hundreds of millions to a few billion years. Once formed, they can grow through mergers, but there are limits to how large any individual galaxy can become. Structures like great walls, by contrast, can keep growing as long as the universe allows. They assemble from components that are themselves already large, and the assembly process spans most of cosmic history. A great wall forming today might incorporate material that was initially spread across many separate regions, each of which developed its own clusters and filaments before being drawn together into the larger assembly. The result is a hierarchy of structures, each level larger than the one below. Stars form within galaxies. Galaxies cluster into groups and clusters. Clusters align along filaments. Filaments weave together into walls and sheets. And these walls and sheets may themselves be parts of still larger patterns that we have only begun to glimpse. At each level, the structures are bound or associated by gravity, but the nature of that binding changes. Galaxies are tightly bound systems where stars orbit for billions of years. Clusters are more loosely bound, with galaxies moving within them but rarely escaping. Filaments are barely bound at all, more like streams of matter flowing toward dense regions than coherent objects in their own right. And great walls represent the transition to scales where the expansion of the universe begins to dominate. Within a great wall, gravity still pulls matter together, but the wall itself is being stretched by cosmic expansion. It is not collapsing into a single object. It is a pattern in the flow of matter, a concentration relative to the even emptier voids surrounding it. This distinction matters when comparing great walls to galaxies. A galaxy is a gravitationally bound system. Its stars will remain part of it for billions or trillions of years, barring external disturbances. A great wall is more like a river than a lake. The water flows through it, tracing the path of the current, but the river itself is defined by the landscape rather than by the water molecules it contains at any given moment. Galaxies can be measured by their mass or their diameter and compared directly. Great walls are harder to compare because their boundaries are less defined. Where does one great wall end and another begin? The answer is often ambiguous, depending on how you define membership and what density threshold you use to distinguish structure from void. Despite these ambiguities, researchers have identified several great walls that stand out as particularly impressive. These structures have been named, mapped, and studied with various techniques. Their properties reveal just how much larger the cosmic web is compared to individual galaxies. One structure in particular has received attention because of its apparent extent. Located in a specific region of the sky, this concentration of galaxies and clusters stretches across a distance that challenges our measurement techniques. Even conservative estimates place its length at several billion light-years. To emphasize what this means, let us return to the comparison with individual galaxies. The largest known galaxies measure perhaps 20 million light-years at most, including their extended radio emissions. This Great Wall measures thousands of times longer. If the largest galaxy is a strand of hair, the Great Wall is a transcontinental highway. Yet even this comparison understates the difference, because the Great Wall is not a single linear object. It has depth and width, as well as length. It contains thousands of galaxy clusters, millions of individual galaxies, and countless stars. The total mass within it defies easy comprehension. How did astronomers discover such a structure? The process involved mapping the three-dimensional positions of galaxies across a wide region of sky. By measuring the distance to each galaxy through its redshift, researchers could determine not just where galaxies appeared on the sky, but how far away they were. This allowed them to build up a three-dimensional map of galaxy distribution. When they examined this map, they noticed that galaxies were not scattered randomly. They clustered along certain directions, forming patterns that extended across vast distances. By tracing these patterns, they identified the filaments and walls of the cosmic web in this region. The Great Wall emerged as a particularly prominent feature, a concentration of matter that stood out against the surrounding voids. Further observations confirmed that the galaxies within it were not just aligned by chance. They were physically connected by the same filaments, and drawn toward the same gravitational centers. This discovery built on earlier work that had identified other great walls and filaments. Each new survey extended the map further, revealing structures at larger and larger scales. The cosmic web, once a theoretical prediction, became an observed reality, documented in detailed catalogs. But here is something that deserves attention. Even as these structures were being mapped, some researchers began questioning whether we had found the largest ones. What if there were patterns on scales even greater than the great walls already cataloged? What if the cosmic web itself had structure at scales we had not yet measured? This question has not been fully answered. The observable universe has a finite size, limited by the distance light has had time to travel since the beginning of cosmic history. Beyond a certain radius, we cannot see anything, no matter how powerful our telescopes. This means there is a fundamental limit to the largest structure we could ever observe. But within the observable universe, there is room for structures much larger than those already discovered. Our surveys have covered only a fraction of the sky to the necessary depth. Vast regions remain poorly mapped. The great walls we know might be parts of even greater assemblies that span most of observable space. Recent research has begun exploring this possibility. Using advanced statistical techniques, astronomers have searched for correlations in galaxy positions that would indicate structure at the largest scales. Some of these studies have found hints of patterns extending across 10 billion light-years or more. If confirmed, such patterns would represent structures nearly as large as the observable universe itself. They would not be coherent objects in the way a galaxy or even a cluster is coherent, but they would be real patterns in the distribution of matter, reflecting the initial conditions of the universe and the physics of structure formation. The discovery of such patterns would push our understanding of cosmic structure to its ultimate limits. It would also raise profound questions about the nature of the universe and the processes that shaped it. For now, let us focus on what we know with greater certainty. The cosmic web is real. Its filaments and walls have been mapped across billions of light-years, and these structures make even the largest individual galaxies appear small by comparison. This is the discovery that reframes our understanding. Not a single bigger galaxy waiting to be found, but a recognition that galaxies themselves are components of something far more vast. The biggest galaxy is still impressive, but it is impressive in the way that the largest tree in a forest is impressive. The forest itself extends beyond any single tree. With this framework in mind, let us explore some of the specific structures that astronomers have identified. Each one illustrates a different aspect of the cosmic web and its overwhelming scale. The first example worth considering is a structure located in the northern sky, visible from observatories in the northern hemisphere. This structure was among the first great walls discovered and remains one of the best studied. When astronomers mapped the galaxies in this region, they found a concentration stretching across hundreds of millions of light-years. The galaxies within it formed long chains connected by bridges of fainter objects. At the densest points, galaxy clusters containing thousands of members anchored the overall structure. What made this wall remarkable was not just its size, but its coherence. The galaxies within it appear to be part of a connected system, moving together under the influence of shared gravitational fields. This suggested that the wall was not just a chance alignment, but a genuine physical structure. Subsequent observations confirmed this interpretation. The gas between galaxies in the wall proved to be hotter than in surrounding regions, heated by the gravitational compression that comes with dense environments. The dark matter distribution, mapped through gravitational lensing, showed a continuous scaffolding underlying the visible galaxies. This wall extends across a distance that light takes several 100 million years to traverse. Within it reside multiple galaxy clusters, each comparable to the largest gravitationally bound structures in the universe. The total mass contained within the wall exceeds that of millions of individual galaxies like our own. Yet this wall is not the largest structure known. Other surveys have found concentrations extending even further. Some appear to stretch across more than 1 billion light-years, though measuring such extreme distances introduces significant uncertainties. The second example comes from a different region of the sky, identified through surveys that used gamma-ray observations to map the distribution of matter. In this region, astronomers found an apparent overdensity of gamma-ray bursts, energetic explosions that occur in distant galaxies. Gamma-ray bursts happen throughout the universe, wherever massive stars collapse or neutron stars collide. By mapping where these bursts occurred, astronomers could indirectly trace the distribution of galaxies. What they found suggested a structure of extraordinary dimensions, potentially spanning several billion light-years. This structure, if confirmed as a genuine physical concentration rather than a statistical artifact, would be among the largest ever identified. It would contain matter equivalent to billions of large galaxies, spread across a volume so vast that no single object within it could gravitationally influence the whole. The debate over this structure illustrates an important point. At the largest scales, identifying genuine structures becomes increasingly difficult. Random fluctuations in galaxy distribution can mimic the appearance of coherent assemblies. Distinguishing real patterns from noise requires careful statistical analysis and independent confirmation. This is why astronomers remain cautious when claiming new records for cosmic structure size. The biggest structures are the hardest to verify precisely because of their size. A structure spanning billions of light-years can only be seen in full by surveys covering significant fractions of the sky to great depth. Such surveys are expensive and time-consuming. The data they produce requires years of analysis. Despite these challenges, the overall picture remains clear. The universe contains structures far larger than any individual galaxy. These structures are not hypothetical or speculative. They have been detected through multiple independent methods. Their properties have been measured and compared to theoretical predictions. The cosmic web is as well established as any feature of the universe. And within this web, the hierarchy continues. Great walls contain superclusters. Superclusters contain clusters. Clusters contain galaxies. Galaxies contain stars and planets and clouds of gas. Each level nests within the next, like Russian dolls of cosmic dimension. Understanding this hierarchy helps explain why individual galaxies, even the very largest, occupy such a modest position in the overall scheme. A galaxy is impressive within its context. Compared to a single star, it is overwhelming. Compared to a cluster, it is still substantial. But compared to the great walls and filaments of the cosmic web, it is a single link in an endless chain. This is not meant to diminish galaxies. They remain fascinating objects, worthy of study and admiration. The processes that shape them, from star formation to supermassive black hole growth, reveal fundamental aspects of physics. Understanding how galaxies form and evolve is essential for understanding the universe. But perspective matters. When we ask what the biggest structures in the universe are, we must be clear about what level of the hierarchy we are considering. Within the category of individual galaxies, some are much larger than others. Within the category of structures in the cosmic web, some are much larger than others too. But the categories themselves differ so greatly in scale that comparing across them requires care. The biggest galaxy is bigger than most galaxies. The smallest Great Wall is bigger than the biggest galaxy. The largest Great Wall is bigger than most Great Walls. And the cosmic web as a whole dwarfs everything within it. This is the proper context for understanding cosmic size. Not a single object claiming the title of biggest, but a hierarchy of structures spanning every scale from stellar to cosmological. With this context established, let us delve deeper into the physics that governs these structures. Understanding why the cosmic web exists and why it takes the forms we observe illuminates the fundamental forces shaping the universe. The story begins in the very early cosmos, long before any galaxies or stars existed. At that time, the universe was nearly uniform. Matter and radiation filled space with almost perfect smoothness, but not quite perfect. Tiny variations in density, so small they can only be described in parts per 100,000, were imprinted on the early universe. These variations originated in quantum fluctuations during the first instance after the beginning, amplified by the subsequent expansion of space. For hundreds of thousands of years, these variations remained frozen. The universe was too hot and dense for gravity to act effectively. Radiation pressure pushed back against any attempt by matter to collapse. The density variations persisted but did not grow. Then came a transition. As the universe expanded and cooled, radiation decoupled from matter. Photons, the particles of light, began to stream freely through space. Matter was left behind, no longer supported by radiation pressure, free to respond to gravity. Now the tiny density variations could begin to grow. Regions with slightly more matter pulled in their surroundings. Regions with slightly less lost material to their denser neighbors. Over millions of years, contrast built up. The slightly overdense regions became more overdense. The slightly underdense regions became more underdense. This process, called gravitational instability, is the engine that built the cosmic web. It took primordial variations, subtle patterns imprinted in the first moments, and amplified them over billions of years into the structures we see today. But gravity alone does not explain the specific form of the cosmic web. Why filaments and walls? Why not just spherical blobs of matter scattered through space? The answer involves the geometry of collapse. When matter falls inward under gravity, it does not necessarily fall symmetrically. If a region is slightly elongated, matter preferentially collapses along the short axis first. An elongated cloud becomes more elongated as it collapses, eventually forming a flattened sheet. If the initial region is even more asymmetric, collapse proceeds along two axes before the third. The result is an elongated filament rather than a flat sheet. These tendencies explain why the cosmic web has its characteristic appearance. Spherical collapse is rare because it requires perfectly symmetric initial conditions. Most regions have some asymmetry, leading to sheets and filaments as the natural outcome. The nodes where filaments meet form through a different process. When filaments carrying matter toward a common center converge, their flows pile up at the intersection. The result is a dense knot of matter, which becomes a galaxy cluster. Clusters then form at the intersections of filaments. Filaments form along the boundaries between expanding voids. And voids form in regions where matter has drained away toward the surrounding structures. This is the physics of the cosmic web. It is remarkably simple in principle, governed by nothing more than gravity and the geometry of initial conditions. Yet it produces structures of staggering complexity, from the delicate filaments threading through voids to the massive clusters anchoring the web. Understanding this physics helps explain why the cosmic web exhibits structure at all scales. The initial density variations spanned a range of sizes. Large variations seeded large structures. Small variations seeded small structures. The resulting web inherits this multi-scale character, with patterns visible from kiloparsecs to gigaparsecs. It also helps explain why there are limits to structure size. The universe has expanded for only about 14 billion years. Light and gravity can only travel a certain distance in that time. Structures larger than this distance cannot be gravitationally coherent. They cannot have influenced their entire extent through gravitational interaction. This is why the largest great walls are not gravitationally bound systems. They are patterns in the distribution of matter, concentrations relative to the average, but not collapsed objects held together by mutual attraction. Gravity has shaped them, but expansion prevents them from holding together as single units. The distinction matters when comparing structures at different scales. Galaxies are bound. Clusters are bound. Most filaments are not quite bound, but are coherent flows of matter falling toward bound structures. And great walls represent the transition to scales where cosmic expansion dominates over gravitational contraction. At these largest scales, the structures we see are fossils of the initial conditions. They preserve information about the patterns imprinted in the early universe, stretched and amplified, but not fundamentally reorganized by subsequent evolution. This is why studying the cosmic web teaches us about cosmology, not just astronomy. The patterns we observe carry echoes of the earliest moments. By mapping these patterns precisely, we can learn about the physics that governed the universe when it was less than a second old. Modern surveys aim to do exactly this. By measuring the positions and motions of millions of galaxies, astronomers can reconstruct the three-dimensional structure of the cosmic web. Statistical analysis of these structures reveals subtle patterns that constrain models of the early universe. These constraints have already yielded important insights. They confirm that the universe is dominated by dark matter and dark energy, substances whose nature remains mysterious, but whose effects are clearly visible in cosmic structure. They show that the initial density variations were nearly scale invariant, with similar amplitudes at all sizes, a prediction of inflationary models. And they reveal that gravity has operated according to the same laws throughout cosmic history, a test of general relativity at the largest accessible scales. Future surveys will extend these measurements further. New telescopes under construction will map billions of galaxies across most of the sky. The resulting data will provide the most detailed picture yet of the cosmic web and its properties. What might these surveys reveal? Perhaps they will confirm the existence of structures at the very largest scales. patterns spanning most of observable space. Perhaps they will find unexpected features that challenge current models. Perhaps they will simply refine our existing understanding, filling in details without changing the overall picture. Whatever the outcome, the enterprise is remarkable. Humans, confined to a small planet orbiting an ordinary star, have learned to map structures extending across billions of light years. We have discovered that our universe is woven together by a web of matter and energy, shaped by forces operating since the beginning of time. This is the context in which the biggest galaxy must be understood. It is a notable object, larger than most galaxies by a significant margin, but it exists within a cosmic web that dwarfs it completely. The web is not just bigger, it is the framework within which galaxies themselves make sense. The discovery that makes the biggest galaxy look small is not a single finding, but a shift in perspective. We have learned to see galaxies as components of larger structures. We have measured those structures and found them to span billions of light years. And we have recognized that the concept of biggest depends on what level of the hierarchy you are considering. At the level of individual galaxies, records matter. Astronomers track which galaxy has the largest diameter, the most massive black hole, the fastest star formation rate. These records are interesting and important. They mark the extremes of what the universe can produce within the category of galaxies. But at the level of the cosmic web, individual galaxies are details. The structures that matter are the filaments and walls and clusters, the patterns that organize galaxies into networks spanning observable space. Records at this level are harder to define because boundaries are fuzzy and scales are vast. But the structures themselves are no less real. Between these levels, a fascinating transition occurs. Some structures are clearly galaxies. Some are clearly large-scale cosmic web features. But others sit in between, blurring the boundaries. Consider galaxy clusters. Are they individual objects or small parts of the cosmic web? The answer is both. A cluster is the largest gravitationally bound structure in the universe, a single system held together by gravity. But it is also a node in the cosmic web, the point where filaments converge and matter accumulates. This dual nature makes clusters particularly interesting. They are massive enough to influence their surroundings significantly, attracting galaxies from the filaments that feed them. Yet they are also embedded in those filaments, shaped by the flows of matter along the cosmic web. Studying clusters reveals information about both levels of the hierarchy. Their internal properties, like the distribution of galaxies or the temperature of intra-cluster gas, tell us about the physics of collapsed objects, their positions and connections, how they relate to surrounding filaments and other clusters. Tell us about the larger structure of the web. Some clusters are particularly massive, containing many thousands of galaxies and enormous amounts of dark matter and hot gas. These massive clusters sit at the most prominent nodes of the cosmic web, where multiple large filaments converge. They represent local maxima in the density field, the densest regions within their neighborhoods. The most massive clusters have masses exceeding 1,000 trillion times that of our star. This is far more than any individual galaxy, even the largest. A single cluster can contain many large galaxies, plus countless smaller ones, all bound together by their combined gravitational influence. Yet even these most massive clusters are small features within great walls. A great wall might contain dozens of massive clusters connected by filaments stretching across distances that would take light hundreds of millions of years to traverse. The cluster is immense by any reasonable standard. The wall is immense by even more extreme standards. This nesting of scales continues as far as we can measure. Every time astronomers develop the capability to observe larger volumes, they find structures filling those volumes. The universe appears to have structure at every accessible scale, from the subatomic to the cosmological. Whether this continues beyond what we can observe remains unknown. The universe might extend infinitely, with structure at all scales no matter how far you look. Or it might have a finite size, with the largest structures comparable to the whole. We cannot know from inside our observable bubble. What we can know is that within that bubble, the hierarchy of structures is real and measurable. And at every level, except the very largest, there are bigger things waiting above. This returns us to the question of what counts as big. The biggest galaxy is big by galaxy standards, but it is small by cosmic web standards. Great walls are big by any standard available to us, but they might be small compared to structures beyond our observable horizon. Size is relative. Context determines meaning. And the context provided by the cosmic web is one of almost incomprehensible vastness. Let me describe one more aspect of these structures before moving on. We have discussed their sizes and how they formed, but we have not yet considered how they change over time. The cosmic web is not static. It evolves continuously as matter flows along filaments, clusters grow, and voids expand. This evolution happens slowly by human standards, but rapidly by cosmic standards. Consider a filament connecting two galaxy clusters. Matter within the filament is falling toward one cluster or the other, drawn by their gravitational attraction. Galaxies embedded in the filament drift along with this flow, gradually moving toward whichever cluster exerts stronger pull. Over billions of years, this flow significantly changes the filament. Galaxies that were far from either cluster move closer to one or the other. The filament becomes narrower as matter drains toward its endpoints. Eventually, the filament might disappear entirely, all its matter having fallen into the clusters it once connected. Meanwhile, the clusters themselves are growing. Each new galaxy that falls in adds to their mass. Each new increment of mass increases their gravitational reach. The most massive clusters become even more massive, drawing material from ever greater distances. This process has a name: hierarchical structure formation. Small things merge to form larger things. Larger things merge to form even larger things. Over time, the typical mass of the densest objects increases. We see this process in action when we observe the universe at different distances. Because light takes time to reach us, looking at distant objects means looking at younger versions of the universe. Nearby galaxies and clusters show us the universe as it is now. Distant galaxies and clusters show us the universe as it was billions of years ago. When astronomers compare nearby and distant clusters, they find systematic differences. Nearby clusters are larger and more massive on average. Distant clusters are smaller and less massive. This matches the prediction of hierarchical structure formation. Clusters grow over time by accreting matter and merging with other clusters. Great walls show similar evolution, though the changes are subtler. Walls identified at great distances appear slightly different from nearby walls. The exact nature of these differences is still being studied, but the general pattern matches theoretical expectations. Looking to the future, the cosmic web will continue to evolve. Matter will continue flowing along filaments, clusters will continue growing, voids will continue emptying. But eventually, this evolution will slow and eventually stop. The acceleration of cosmic expansion, driven by dark energy, is gradually pulling structures apart. Filaments are being stretched. Flows are being disrupted. In the distant future, structures beyond a certain size will no longer be able to hold together. Clusters and the galaxies within them are dense enough to resist this expansion. They will remain bound for the foreseeable future, held together by gravity despite the expansion of surrounding space. But the larger structures, the filaments and walls and great patterns of the web, will gradually disperse. Billions of years from now, the cosmic web will begin to dissolve. Filaments will fade as their matter falls into clusters or dissipates into expanding voids. The connections between clusters will attenuate and break. Eventually, each cluster will be isolated, unable to see other clusters as they recede beyond the cosmological horizon. This is the long-term fate of the cosmic web, not a sudden destruction, but a gradual fading, as expansion stretches structures beyond the point of coherence. It is a melancholy vision in some ways. The intricate web that took billions of years to form will take billions more to dissolve. The universe will become simpler, less structured, more homogeneous. The era of complexity will give way to an era of isolation and darkness, but that fate lies far in the future, so distant that it has little bearing on our current experience. For now, the cosmic web remains vibrant and intricate. Great walls stretch across billions of light years. Filaments channel matter toward hungry clusters. Voids expand and merge into ever larger empty regions. The universe is still in its structured prime, and at the nodes and along the filaments of this web, galaxies shine. Some are small, containing only millions of stars. Some are enormous, spanning millions of light years, with their halos of matter and energy. Each one is a world unto itself, a collection of stars and planets and possibilities. The biggest among them are impressive by any measure. They represent the extremes of galactic growth, the outcomes of countless mergers, and eons of accumulation. They have swallowed many smaller galaxies over their histories. They may swallow many more before their growth ends. But even the biggest galaxy is just one node among countless others. Even the biggest cluster is just one intersection among countless others. The cosmic web extends beyond any single object, beyond any category of objects, encompassing the observable universe in its threads and voids. This is the discovery that makes the biggest galaxy look small. Not a single observation or measurement, but an entire framework for understanding cosmic structure. Within that framework, individual galaxies occupy an important but limited role. They are the building blocks, the luminous tracers, the places where stars form and intelligent observers might arise. But they are not the whole story. The whole story includes filaments that feed them, clusters that contain them, walls that organize them, and voids that separate them. It includes dark matter that scaffolds them, and dark energy that will eventually isolate them. It includes the initial conditions that seeded them, and the long evolution that shaped them. To understand cosmic structure is to understand all of this, not just the individual pieces, but how those pieces fit together. And when you see the full picture, when you grasp the hierarchy of scales from stars to galaxies to clusters to walls to the web itself, then the biggest galaxy takes its proper place. It is remarkable. It is extreme. But it is not alone. And it is not the ultimate answer to what the universe can build. The ultimate answer, if there is one, lies in the cosmic web as a whole. And the web is still being explored, still being mapped, still revealing surprises. What we know today is substantial, but what we will learn tomorrow may be more substantial still. Perhaps future surveys will find structures that dwarf even the greatest walls we currently know. Perhaps they will find unexpected patterns at the largest scales, features that challenge our models, or confirm them in surprising ways. The universe has shown a consistent tendency to exceed our expectations. There is no reason to think that tendency has ended. For now, we can appreciate what we have learned. The cosmic web is real. It spans the observable universe. It contains structures at every scale, from small galaxy groups to great walls billions of light years across. And within it, the biggest galaxies shine brightly, impressive in their way, but small compared to the fabric that contains them. This is the proper understanding of cosmic size. Not a competition between individual objects, but an appreciation of how objects nest within larger structures, which nest within larger structures still, up to the largest scales we can observe. The biggest galaxy is big. The cosmic web is bigger. And the universe itself is biggest of all, containing both in its endless reaches. With this foundation established, let us turn our attention to specific aspects of the cosmic web that illuminate its nature and properties. Each aspect offers a different window into this vast structure, revealing details that help complete the picture. We will begin with dark matter, the invisible substance that forms the skeleton of the cosmic web. Then, we will explore the gas that fills filaments and clusters, the visible tracer of underlying structure. We will examine how galaxies move within the web, tracing flows that reveal gravitational fields. And we will consider the voids, the empty regions that define the web by their absence. Each of these topics deserves extended attention. Together, they paint a portrait of the cosmic web in all its complexity. Dark matter is perhaps the strangest character in this story. We have never detected it directly. We do not know what particle or field it consists of. Yet we are confident it exists because its gravitational effects are unmistakable. The story of dark matter begins in the 1930s when an astronomer studying galaxy clusters noticed something puzzling. The galaxies within clusters were moving faster than expected. Based on the visible mass in the cluster, they should have been moving slowly enough to remain bound. Instead, they were moving so fast that they should have escaped long ago. Either the galaxies were not actually bound to the cluster, which seemed implausible given their obvious concentration, or some additional mass was present that was not visible. The astronomer proposed this second explanation, calling the unseen material dark matter. For decades, this proposal remained controversial. Perhaps the galaxy's motions had been misinterpreted. Perhaps the laws of gravity behave differently at large scales. Various explanations were proposed, each with proponents and skeptics. But as evidence accumulated, the case for dark matter strengthened. Galaxy rotation curves, the speeds at which stars orbit within galaxies, showed similar discrepancies. Stars in the outer parts of galaxies were moving too fast given the visible mass. Unless additional invisible mass was present, they should have been flying off into intergalactic space. gravitational lensing provided another line of evidence. Massive objects bend light from background sources, distorting their images. By measuring these distortions, astronomers could map the distribution of mass responsible for them. When they did, they found mass extending far beyond the visible galaxies, distributed in halos that could not be accounted for by stars and gas alone. The cosmic microwave background, the faint radiation left over from the early universe, provided still more evidence. Subtle patterns in this radiation reflect the density variations that seeded cosmic structure. The characteristics of these patterns depend on the relative amounts of ordinary matter, dark matter, and dark energy. The best match to the observed patterns requires about 5 times as much dark matter as ordinary matter. Taken together, this evidence is overwhelming. Dark matter exists. It outweighs ordinary matter by a substantial margin, and it forms the scaffolding of the cosmic web. But what is dark matter made of? This remains one of the biggest open questions in physics. Various candidates have been proposed, from exotic particles like WIMPs, weakly interacting massive particles, and axions to primordial black holes formed in the early universe. Experiments around the world are searching for these candidates. Deep underground detectors wait patiently for the rare collision between a dark matter particle and an ordinary nucleus. Particle accelerators attempt to produce dark matter under controlled conditions. Telescopes scan the sky for signatures that would reveal dark matter's particle nature. So far, no definitive detection has been made. We know dark matter exists from its gravitational effects, but we do not know what it is made of. This is a profound gap in our understanding, one of the great mysteries of modern science. For our purposes, what matters most about dark matter is its role in the cosmic web. Dark matter dominates the gravitational field at large scales. It determines where galaxies form and how they move. The filaments and walls of the cosmic web are primarily dark matter structures, with ordinary matter following along. Simulations of cosmic structure formation illustrate this clearly. When researchers model the evolution of the universe, including both dark matter and ordinary matter, they find that dark matter clumps first. Ordinary matter, initially too hot to collapse, follows later, falling into the gravitational wells created by dark matter. The result is a web of dark matter filaments connecting dense dark matter halos. Galaxies form within these halos, where ordinary matter can cool and condense into stars. The visible cosmic web, traced by galaxies, is a luminous overlay on the underlying dark matter structure. This means that the structures we see, the filaments and walls and clusters, are only part of the true cosmic web. The full web includes all the dark matter that we cannot see directly, but can detect through its gravitational influence. Mapping this dark matter web has become a major goal of observational cosmology. By measuring gravitational lensing across wide areas of sky, astronomers can reconstruct the distribution of matter regardless of whether it emits light. These maps reveal the dark matter structure in unprecedented detail. What they show confirms theoretical predictions. Dark matter forms filaments and halos, just as simulations suggest. The positions of galaxies correlate strongly with the dark matter distribution. The visible and invisible components of the cosmic web are intimately connected. One striking finding from these maps concerns the extent of dark matter halos. Every galaxy sits within a halo of dark matter, extending far beyond its visible borders. For a galaxy like our own, the dark matter halo might extend hundreds of thousands of light years from the center, far beyond the outermost stars. For larger galaxies and galaxy clusters, the halos are proportionally larger. A massive cluster might have a dark matter halo extending tens of millions of light years from its center. This halo contains most of the cluster's mass, dwarfing the visible galaxies within it. When we ask how big structures in the universe are, we must account for these dark matter halos. A galaxy that appears to span a certain diameter visually actually influences a much larger region through its dark matter. The gravitational reach of the structure extends well beyond its luminous edge. This makes comparisons between structures more complex. The biggest galaxy by visible extent might not be the biggest by dark matter halo size. The two measures can disagree significantly, especially for galaxies in different environments. Galaxies in dense regions tend to have truncated dark matter halos. The gravitational influence of nearby neighbors strips material from the outer parts of the halo, reducing its extent. Galaxies in isolated regions can retain more extended halos, spreading their gravitational influence over larger volumes. This environmental dependence adds another layer to our understanding of cosmic structure. Galaxies are not independent objects floating in empty space. They are embedded in a web of dark matter, shaped by their surroundings. Their sizes determined not just by internal properties, but by external context. The biggest galaxy, whatever we take that to mean, exists within this context. Its dark matter halo extends beyond its visible borders. That halo connects to neighboring halos through filaments of dark matter. Those filaments are part of larger structures, which are part of still larger structures. The boundary between the galaxy and its surroundings is not sharp, but gradual. A transition from higher to lower density within a continuous web. This is another way in which the cosmic web makes the biggest galaxy look small. The galaxy's gravitational influence fades gradually into its surroundings. There is no hard edge where the galaxy ends and the web begins. Instead, there is a continuous structure in which the galaxy is just a local concentration. Understanding dark matter also helps explain how the cosmic web will evolve in the future. Dark matter responds to gravity, but not to radiation pressure or other forces that affect ordinary matter. Its evolution is simpler, governed primarily by gravitational dynamics. Simulations running far into the future show that dark matter halos will continue to merge and grow. The most massive clusters will become even more massive as they absorb neighboring systems. But eventually, the expansion of space will isolate these systems from each other. The cosmic web will fragment into separate islands, each containing its own dark matter concentration. This is the long-term fate we discussed earlier, now seen through the lens of dark matter physics. The web does not dissolve because dark matter disperses. It fragments because expansion pulls its components apart. Each fragment remains dense and gravitationally bound, but the connections between fragments attenuate and break. Dark matter provides the framework for this process. It determines which structures survive and which connections fail. The future of the cosmic web is written in the distribution and dynamics of this invisible substance. With dark matter providing the invisible scaffold, let us now consider the gas that fills the cosmic web. This gas is ordinary matter, made of the same particles as stars and planets and our own bodies. But it exists in a very different state, spread thinly through the vast spaces between galaxies. The gas in the cosmic web takes several forms. Within galaxies, gas is relatively cool and dense, capable of collapsing to form stars. Between galaxies and clusters, gas is extremely hot, heated to millions of degrees by gravitational compression. Along filaments, gas is intermediate in temperature and density, warmer than inside galaxies, but cooler than in clusters. This intergalactic gas is difficult to observe because it emits little light. Unlike the gas in star-forming regions, which glows brightly with emission lines, intergalactic gas is mostly ionized and too diffuse to produce strong signals. Detecting it requires specialized techniques. One approach uses absorption lines. When light from a distant source, like a quasar, passes through intergalactic gas, certain wavelengths are absorbed. By analyzing which wavelengths are absorbed and by how much, astronomers can infer the properties of the intervening gas. This technique has revealed a forest of absorption features, hundreds of lines created by gas clouds along the line of sight. Each line corresponds to a different cloud at a different distance, allowing the distribution of gas along the line to be reconstructed. What these observations show is that intergalactic gas traces the cosmic web. The absorption is strongest where filaments cross the line of sight and weakest where voids lie. The gas follows the dark matter, concentrated where matter is dense and sparse where matter is scarce. Another approach uses emission at specific wavelengths. Although intergalactic gas emits weakly, sensitive instruments can detect its glow in favorable circumstances. Recently, astronomers have begun mapping this emission directly, revealing filaments lit up by their own faint radiation. These observations confirm that filaments are not just mathematical constructs or statistical patterns. They are physical structures filled with matter. The gas within them represents most of the ordinary matter in the universe, far more than exists in galaxies themselves. This is a remarkable finding. Galaxies, with all their stars and planets and complexity, contain only a small fraction of the universe's ordinary matter. Most of it exists in intergalactic gas, spread thinly along the filaments and halos of the cosmic web. The gas has been there since nearly the beginning. In the early universe, before any stars formed, ordinary matter existed as a uniform fog of hydrogen and helium. As structure formed, this gas was drawn toward the same regions as dark matter, collecting along filaments and in halos. Some of this gas cooled and collapsed to form galaxies and stars, but most remained diffuse, too hot or too sparse to collapse. It continues to reside in the cosmic web, slowly falling toward dense regions, but never quite getting there. Over cosmic time, this gas plays an important role in galaxy evolution. Galaxies grow by accreting gas from their surroundings. A galaxy at the node of a filament receives a steady stream of fresh material, fuel for new stars. A galaxy in a void receives little, starved of the resources needed for growth. The flow of gas along filaments connects galaxies to their environments. It links the large-scale structure of the cosmic web to the small-scale physics of star formation. Understanding this flow is essential for understanding how galaxies evolve. Simulations of the cosmic web include these gas dynamics, modeling how gas moves and heats and cools within the dark matter framework. The results match observations remarkably well, reproducing the distribution of gas seen in absorption and emission studies. These simulations also reveal complex flows within the web. Gas does not simply fall smoothly toward dense regions. It can be heated by shocks, pushed outward by galactic winds, recycled multiple times through galaxies, and back into intergalactic space. The interplay between infall and outflow determines how much gas ends up in stars and how much remains in the web. The hot gas in galaxy clusters deserves special mention. When gas falls into a cluster's deep gravitational well, it is compressed and heated to extreme temperatures. This intracluster medium, as it is called, reaches temperatures of tens of millions of degrees, far hotter than the surface of any star. At these temperatures, the gas emits X-rays, which can be detected by space-based telescopes. X-ray observations have mapped the hot gas in many clusters, revealing its distribution and temperature structure. What these observations show is that hot gas fills the space between cluster galaxies. The gas is smoothly distributed, shaped by the cluster's gravitational field. Its mass often exceeds the combined mass of all the cluster's galaxies, making it the dominant baryonic component of the cluster. This hot gas traces the shape of the dark matter halo. Where dark matter is concentrated, gas temperature and density are higher. Where dark matter is sparse, gas is cooler and thinner. The two components are intimately connected, both shaped by the same gravitational field. The hot gas also acts as a calorimeter, recording the energy released during cluster formation. As galaxies and groups fall into the cluster, their kinetic energy is converted to heat. The current temperature of the gas reflects the total energy deposited over the cluster's history. By measuring this temperature, astronomers can estimate the cluster's mass. This technique provides an independent check on other mass estimates, from gravitational lensing or galaxy velocities. The results generally agree, confirming our understanding of cluster structure. The gas in the cosmic web, both the hot gas in clusters and the cooler gas in filaments, represents ordinary matter in its most common cosmic state. We are made of this stuff, but in us it is cold and dense and organized into complex structures. In the web, it is hot and sparse and formless. This contrast highlights how unusual galaxies are. They are rare concentrations of matter within a vast and diffuse web. The conditions inside them differ enormously from the conditions outside. Stars can only form where matter is dense enough and cool enough to collapse. Most of the web never reaches these conditions. The cosmic web is therefore mostly dark and empty by terrestrial standards. The filaments contain gas, but that gas is spread so thinly that a cubic meter of filament space contains fewer atoms than the best vacuum chambers on Earth. The web is there, but it is subtle, more absence than presence. Yet this subtle presence shapes everything else. The gas flows drive galaxy growth. The gravitational field of the dark matter determines where galaxies form. The hot gas in clusters prevents further star formation in galaxies that fall within. The cosmic web is the invisible stage on which cosmic drama plays out. The biggest galaxy exists on this stage. Its properties reflect not just internal processes, but its relationship to the surrounding web. It grew large because filaments fed it matter. It stopped growing because that flow eventually weakened. Its size tells us as much about its environment as about itself. This environmental perspective is essential for understanding cosmic structure. Objects do not exist in isolation. They are embedded in context, shaped by surroundings, connected to neighbors through threads of matter and gravity. The web is not just a backdrop, but an active participant in cosmic evolution. The gas within the web carries other information as well. Elements heavier than hydrogen and helium, forged in stars and dispersed through supernova explosions, are scattered through intergalactic space. By measuring the abundances of these elements, astronomers can trace the history of star formation and chemical enrichment. Surprisingly, even gas, far from any galaxy, contains traces of heavy elements. This suggests that galactic winds, outflows driven by star formation, and supermassive black hole activity have spread material throughout the web. Galaxies are not closed systems. They exchange matter with their surroundings, polluting the intergalactic medium with their products. This chemical enrichment connects the history of stars to the history of the cosmic web. The oxygen and carbon and iron floating in distant filaments were once inside stars, produced by nuclear fusion, expelled in explosions, carried across space by winds. The web carries a record of all this activity, preserved in the composition of its gas. The cosmic web is therefore not just a structure, but an archive. It records the history of matter in the universe, from the primordial hydrogen that emerged from the early cosmos to the heavy elements produced by countless generations of stars. Reading this archive requires careful observation and sophisticated interpretation, but the information is there for those with the tools to extract it. With dark matter and gas examined, let us turn to the motion of galaxies within the cosmic web. These motions reveal the gravitational field and the flows of matter that shape the web's evolution. Every galaxy is moving. Our own galaxy travels through space at hundreds of kilometers per second, relative to the cosmic microwave background, the frame defined by the radiation left over from the early universe. Other galaxies have their own velocities, some faster, some slower, in various directions. Part of this motion is due to cosmic expansion. Galaxies recede from each other as space itself stretches. This recession is systematic, with more distant galaxies receding faster, following the pattern known as Hubble's law. But superimposed on the systematic expansion are peculiar velocities, motions caused by gravitational attraction to nearby masses. Galaxies do not simply ride the expansion. They also fall toward overdense regions and away from underdense ones. These peculiar velocities carry information about the distribution of mass. By measuring how galaxies deviate from pure expansion, astronomers can infer where mass is concentrated. The flows reveal the gravitational field, which in turn reveals the cosmic web. Large-scale velocity measurements have identified coherent flows extending across vast distances. Galaxies over wide regions of sky share a common drift, falling together toward some massive concentration of matter. The most famous such flow involves our own neighborhood. Thousands of galaxies, including our own, are falling toward a region of enhanced density, known as the Great Attractor. This flow has been measured precisely, revealing a concentration of mass millions of light years away that is pulling galaxies toward it. But the Great Attractor is not the end of the story. Even the Great Attractor, along with our local group and countless other galaxies, is flowing toward an even larger concentration. This hierarchical flow reflects the hierarchical structure of the cosmic web, with smaller flows embedded within larger ones. By mapping these flows across the observable universe, astronomers have reconstructed the underlying mass distribution. What they find matches the web revealed by galaxy counts and gravitational lensing. Flows converge toward filaments and clusters. They diverge from voids. The motion of galaxies traces the skeleton of the web. These velocity studies have also revealed the extent of superclusters, the structures intermediate between clusters and great walls. A supercluster is defined not just by overdensity, but by coherent flow, a region within which galaxies are falling toward a common center. Our own supercluster, called Laniakea, was defined using precisely this criterion. By mapping peculiar velocities across a wide region, researchers identified the watershed, the boundary where flows divide, going toward Laniakea on one side and toward other attractors on the other. Within this watershed, all galaxies are falling toward the same convergence point. Laniakea extends across hundreds of millions of light years, containing our own galaxy, along with thousands of others. It represents our cosmic neighborhood at a large scale, the supercluster within which we reside. But Laniakea itself is part of larger structures. It connects to neighboring superclusters through filaments. Those superclusters connect to others, forming chains and walls at still larger scales. The hierarchy continues upward until it merges with the structures of the cosmic web. Velocity measurements thus provide another window on cosmic structure, complementary to position measurements. Position tells you where galaxies are. Velocity tells you where they are going. Together, they reveal the dynamics of the web, not just its current state, but its evolution. The flows within the web are not random. They follow predictable patterns based on the distribution of mass. Galaxies fall toward overdensities and away from voids. The flows are strongest where mass contrasts are greatest, and weakest where mass is more uniform. These flows also slow over time as cosmic expansion accelerates. The pull of gravity must fight against the stretching of space. In the far future, flows between distant structures will cease entirely as expansion overwhelms gravitational attraction. For now, the flows continue, reshaping the cosmic web bit by bit. Each galaxy that falls into a cluster adds to the cluster's mass. Each bit of matter that leaves a void makes the void emptier. The web evolves through these countless small movements, driven by gravity, constrained by expansion. The biggest galaxy participates in these flows like any other. It is falling toward some larger concentration, just as smaller galaxies fall toward it. Its velocity reflects its position within the web, the gravitational influence of its neighbors, the cosmic expansion that carries it along. Nothing in the web is stationary. Everything moves. The structures we see are snapshots of a dynamic system, frozen in time by the finite speed of light. What we observe now is the web as it was, when the light we detect left its sources millions or billions of years ago. By now, everything has shifted, moved by flows we can only infer. This temporal aspect adds another dimension to our understanding. The cosmic web exists not just in space, but in time, a structure that evolves and changes, shaped by processes that operate across billions of years. Having explored dark matter, gas, and galaxy motions, let us now consider the voids, the empty regions that define the cosmic web by their absence. Voids are the inverse of clusters and filaments. Where those structures represent concentrations of matter, voids represent deficiencies. They are the bubbles in the cosmic foam, the regions from which matter has drained away. Voids are genuinely empty by cosmic standards. A typical void might contain only 1/10 the average density of the universe. This is not a perfect vacuum, but it is sparse beyond any terrestrial comparison. If you could somehow stand inside a void and look around, you would see few galaxies in any direction. The nearest concentration of matter might be millions of light years away. Voids are also enormous. A typical void spans tens of millions of light years across. The largest known voids approach hundreds of millions of light years in diameter. Within them, a space is eerily empty, hosting only scattered dwarf galaxies and thin wisps of gas. The existence of voids is a necessary consequence of structure formation. As matter collected along filaments and in clusters, it left behind the regions from which it came. Those depleted regions became voids. The web and the voids defined each other, matter flowing out of some regions and into others. This process continues today. Voids are still expanding, their boundaries pushed outward as matter at their edges falls toward nearby structures. The expansion of voids is faster than the general expansion of space because matter within them exerts less gravitational pull. In the far future, voids will dominate the universe. As expansion continues, the structures between voids will thin and fragment. Eventually, most of space will be void, with matter concentrated in isolated clumps separated by vast emptinesses. But for now, voids and structures coexist, defining each other through contrast. The filaments of the cosmic web are visible because they stand out against the voids. The voids are identifiable because they differ from the filled regions around them. Voids are not featureless. Within them, faint structures can sometimes be detected. Thin walls and threads of galaxies trace the interior, remnants of the initial density field that never quite collapsed. These structures are subtle, visible only in the deepest surveys, but they show that voids are not perfectly empty. They retain traces of the cosmic web at lower contrast. The largest voids pose interesting questions. How did regions so large come to be so empty? The answer involves the initial conditions, density variations that happen to leave certain regions slightly underdense from the very beginning. Over billions of years, those slight deficiencies grew into the vast emptinesses we observe today. But the largest voids push against theoretical limits. According to standard models, there should be an upper limit to void size based on how much time has passed since structure began forming. Voids larger than this limit would be difficult to explain, requiring either unusual initial conditions or modifications to our understanding of structure formation. So far, the observed voids fall within theoretical bounds, though some are close to the edge. This agreement provides support for standard cosmological models, while leaving room for future discoveries that might challenge them. Voids also serve as natural laboratories for studying physics in unusual conditions. Within voids, the density of matter is low enough that dark energy dominates the gravitational field. This makes voids sensitive probes of dark energy, the mysterious force driving cosmic acceleration. By measuring how voids evolve over time, astronomers can constrain the properties of dark energy. If dark energy is constant, as in the simplest models, voids will expand in a predictable way. If dark energy changes over time, the expansion will differ. Precision measurements of void properties can distinguish between these scenarios. This is another way in which the cosmic web informs our understanding of fundamental physics. The structures and voids of the web encode information about the forces and substances that govern the universe. By reading these patterns, we learn about physics at the most basic level. The contrast between voids and structures also has implications for the galaxies within them. Galaxies and voids evolve differently from galaxies in dense regions. With fewer neighbors to interact with, void galaxies experience fewer mergers and disturbances. They tend to be smaller and bluer, with ongoing star formation that their cluster counterparts have long since exhausted. This environmental dependence shows that galaxies are shaped by their surroundings. A galaxy's properties depend not just on its mass or age, but on where it sits within the cosmic web. The web is not just a container for galaxies, but an active influence on their evolution. The biggest galaxy probably does not reside in a void. The conditions in voids are not conducive to building such large structures. Instead, it likely sits at a node of the cosmic web, where filaments converge and matter has accumulated over billions of years. This location is not coincidental. The biggest galaxies grow by accreting material from their surroundings. At web nodes, material is plentiful, streaming in along multiple filaments. Galaxies in such locations have the raw material for extreme growth. Galaxies and voids do not. Size and environment are thus connected. The biggest galaxies appear where the cosmic web provides the most resources. Their size is a consequence of their position, a reflection of the web's structure. This returns us to the theme that has run through our exploration. Individual galaxies exist within a larger framework. Their properties reflect that framework. Even the most exceptional galaxy is shaped by its place in the cosmic web. The web itself represents the fundamental structure of the universe at large scales. Its filaments and nodes and voids define the cosmic landscape. Within this landscape, galaxies are features, significant but not primary. The primary structure is the web itself. This is what the discovery of the cosmic web revealed. Not just the existence of large structures, but a framework for understanding all cosmic structure. The web provides context for everything else, from individual stars to the largest galaxy clusters. And when that context is understood, the biggest galaxy takes its proper place. It is remarkable, but it is not the ultimate measure of cosmic size. The web is bigger, and the web contains everything. We have now surveyed the major components of the cosmic web: dark matter, gas, galaxy motions, and voids. Each component contributes to the whole, interacting with the others in complex ways. Together, they form a dynamic system that has evolved over billions of years and will continue evolving for billions more. But there is one more aspect of the cosmic web that deserves attention, perhaps the most important aspect of all. This is the relationship between the web and the fundamental laws of physics that govern the universe. The cosmic web did not arise by accident. It emerged inevitably from the initial conditions and physical laws that govern the early universe. Given those starting points, the web was destined to form. Its existence tells us something profound about the nature of reality. To understand this, consider what was needed for the web to form. First, there had to be matter capable of clumping under gravity. Second, there had to be initial variations in density to seed the clumping. Third, there had to be enough time for gravity to amplify those variations into the structures we observe. All three conditions were met in our universe. Dark matter provided the gravitationally clumping component. Quantum fluctuations during inflation provided the initial density variations. And 14 billion years provided ample time for structure to grow. If any of these ingredients had been missing or significantly different, the cosmic web might not exist. A universe without dark matter would form structures much more slowly, if at all. A universe without initial variations would remain smooth forever. A universe that was much younger would not yet have developed significant structure. The fact that our universe contains a cosmic web tells us that it has the reached ingredients and the right history. The web is not just a feature of our universe. It is a consequence of its fundamental properties. This connection between large-scale structure and fundamental physics runs deep. The properties of dark matter determine how structure grows. The nature of dark energy determines how expansion competes with gravitational collapse. The quantum fluctuations that seeded structure reflect the physics of the earliest moments. By studying the cosmic web, we are therefore studying physics at the most fundamental level. The patterns of filaments and voids encode information about particles and fields and forces. Decoding these patterns is one of the great projects of modern cosmology. Considerable progress has already been made. Observations of the cosmic microwave background have measured the initial density variations with extraordinary precision. Galaxy surveys have mapped the resulting structures across billions of light years. Simulations have shown that standard physics accurately reproduces the observed web. This agreement is both reassuring and remarkable. It shows that our understanding of physics, developed largely from experiments on Earth, applies accurately to the largest scales in the universe. The same laws that govern atoms govern the cosmic web. Physics is universal, but the agreement is not complete. There are anomalies and puzzles that remain unexplained. The nature of dark matter is still unknown. The origin of dark energy is deeply mysterious. The precise physics of inflation, the process that generated initial variations, is still debated. These open questions represent frontiers of knowledge, places where current understanding reaches its limits. Future observations of the cosmic web may help resolve them. By measuring the web with ever greater precision, astronomers can test theories and constrain possibilities. The cosmic web is thus not just a structure to be admired, but a tool for discovery. It carries information about the universe's deepest secrets, waiting to be extracted by those with the skills and instruments to read it. This brings us to a fitting place to pause and reflect on what we have covered. We began with a question about the biggest galaxy and how recent discoveries have reframed our understanding of cosmic size. The answer led us through the hierarchy of structures, from galaxies to clusters to filaments to great walls to the cosmic web itself. At each level, we found structures larger than those below. The biggest galaxy is dwarfed by clusters. Clusters are dwarfed by filaments. Filaments are dwarfed by great walls. And great walls are components of a web that spans observable space. This hierarchy is not just a matter of nesting scales. Each level operates differently. Galaxies are bound by gravity. Clusters are bound by gravity. But filaments are flows more than objects. And great walls are patterns more than systems. The cosmic web integrates all these levels into a coherent whole. It is the framework within which everything else exists. Its properties determine where galaxies form, how they grow, and what they become. The biggest galaxy is big because the web made it big, feeding it matter along converging filaments, placing it at a dense node where growth could proceed. Understanding this framework changes how we think about size and significance. The biggest galaxy is not the ultimate achievement of cosmic structure formation. It is one outcome among many exceptional within its category, but modest compared to the framework itself. This perspective does not diminish the wonder of large galaxies. They remain impressive objects, worthy of study and admiration. But it places them in proper context, as parts of a larger whole, features within a landscape of almost incomprehensible extent. The discovery that makes the biggest galaxy look small is therefore not a single observation, but a change in how we see the universe. It is the recognition that galaxies are nodes in a web, that the web extends across billions of light years, and that the web represents the true large-scale structure of the cosmos. This is a discovery that emerged gradually. From countless observations and simulations and analyses, it did not arrive with fanfare, but accumulated through decades of careful work. Today, it is an established part of our understanding, a foundation for future research. Where that research will lead remains to be seen. The cosmic web still holds secrets. Its largest structures are still being mapped. Its relationship to fundamental physics is still being probed. Each year brings new data, new analyses, new insights. Perhaps future discoveries will reveal structures larger than those we know. Perhaps they will find unexpected patterns that challenge current models. Perhaps they will finally explain the nature of dark matter and dark energy. The universe has shown a consistent ability to surprise us. There is no reason to expect that ability has ended. For now, we can appreciate what we have learned. The universe is woven together by a web of matter and energy. That web extends across the observable cosmos. Within it, the biggest galaxies shine, but they shine as small lights in a vast tapestry. This is the proper understanding of cosmic structure. It is humbling and awe-inspiring in equal measure. It places our own existence within a framework of almost unimaginable scale, and it invites us to continue exploring, to continue learning, to continue expanding our understanding to match the universe's vastness. The biggest galaxy is still out there, shining somewhere in the depths of space. But now we know what surrounds it. Now we understand the context that gives its size meaning. And that understanding represents a kind of growth in ourselves, an expansion of our mental horizons to encompass what the universe has built. Let us continue this journey of understanding. There is much more to explore within the cosmic web, many more details to examine, many more connections to trace. The web is vast, but our curiosity is persistent. Together, they make for an endless exploration. We turn now to consider in greater depth some of the specific structures that have been identified within the cosmic web. Each one illustrates different aspects of large-scale structure and raises different questions for research. The structures we will examine range from relatively nearby, where observations are detailed and precise, to the most distant reaches of the observable universe, where measurements are challenging and conclusions are tentative. Together, they paint a picture of a cosmos organized at every scale, from the local to the cosmological. We begin close to home, with a structure that contains our own galaxy. This will set the stage for understanding more distant and more extreme examples. Our galaxy, the Milky Way, is part of a small group of galaxies called the local group. This group contains a few dozen members, dominated by our galaxy and the Andromeda Galaxy, with numerous smaller companions orbiting around them. The local group is not isolated. It is connected by filaments to neighboring groups and clusters. Together, these form a larger structure called the local supercluster, centered on the Virgo cluster, a massive concentration of galaxies about 50 million light-years from us. For many years, the local supercluster was considered our cosmic address at the largest scale. But recent research has expanded this picture significantly. By mapping peculiar velocities across a wide region, astronomers identified a much larger structure that encompasses the local supercluster, along with several neighboring superclusters. This structure, Laniakea, extends across 500 million light-years and contains the mass of about 100 million billion suns. Within Laniakea, galaxies are flowing toward a common attractor, the gravitational center of the supercluster. This attractor lies roughly 200 million light-years away, in a direction where several large galaxy clusters are concentrated. The identification of Laniakea changed our understanding of our cosmic neighborhood. We are not just part of a small local group within a modest supercluster. We are part of a vast structure spanning hundreds of millions of light-years, connected by flows of matter to distant regions we had not previously associated with our own location. But Laniakea is not the largest structure we are connected to. Beyond its borders lie other superclusters, each with its own attractors and flows. These superclusters are themselves connected by filaments, forming chains and walls at still larger scales. Recent work has suggested that Laniakea might be part of an even larger structure, a basin of attraction that encompasses multiple superclusters. If confirmed, this would push our cosmic address to even grander scales. This progression illustrates how our understanding of cosmic structure has expanded over time. Each generation of astronomers has discovered that the structures they identified were parts of larger wholes. There is no reason to think this progression has ended. Laniakea provides a useful benchmark for understanding the scale of the cosmic web. It is large enough to be impressive, spanning distances that light requires hundreds of millions of years to cross. Yet it is small compared to the greatest structures known, which extend across billions of light-years. If Laniakea is our neighborhood, then the great walls and filaments of the cosmic web are our region, encompassing countless Laniakeas within their extent. And the web itself is our universe, the framework containing all regions. Moving outward from Laniakea, we encounter other superclusters with their own properties and characteristics. Each one represents a local concentration of matter, a node in the cosmic web, where galaxies have accumulated over billions of years. Some of these superclusters are more massive and more densely populated than Laniakea. Some are less so. The distribution of supercluster properties reflects the underlying density variations that seeded cosmic structure, with more extreme variations producing more extreme concentrations. One supercluster that has received considerable attention lies in a direction of the sky where a particularly dense concentration of galaxies is observed. This supercluster contains multiple massive clusters connected by filaments, forming a structure of remarkable complexity. Observations of this supercluster have revealed the flows of gas and galaxies within it, the distribution of dark matter inferred from gravitational lensing, and the hot gas filling the space between clusters. It serves as a laboratory for studying structure formation and action. Beyond individual superclusters, the larger patterns of the cosmic web become apparent. Superclusters are not distributed randomly, but align along preferred directions, forming walls and sheets that extend across hundreds of millions to billions of light-years. These walls represent the largest coherent structures identified in the universe. They are not gravitationally bound, so they do not constitute single objects in the traditional sense, but they are real patterns in the distribution of matter, reflecting the initial conditions and the physics of structure formation. The first Great Wall identified was discovered in the 1980s through surveys that mapped the three-dimensional positions of galaxies. This wall extended across several 100 million light years, far larger than any previously known structure. Since then, numerous other walls have been identified, each with its own extent and characteristics. Some are particularly massive, containing a significant fraction of all the galaxies within their survey volume. Others are more modest, visible mainly as overdense regions against the average background. The largest walls challenge measurement and definition. Where does one wall end and another begin? The boundaries are fuzzy, grading gradually from overdense to underdense regions. Different researchers, using different criteria, may draw boundaries differently. Despite these difficulties, some structures stand out as particularly extreme. One such structure, identified through observations of distant gamma-ray bursts and confirmed by galaxy counts, appears to extend across more than 10 billion light-years. If this measurement is accurate, the structure encompasses a significant fraction of the observable universe. Structures this large raise interesting questions. Are they consistent with standard cosmological models, which predict limits to structure size based on the age of the universe and the properties of dark matter? Or do they require modifications to those models, perhaps involving unusual initial conditions or new physics? So far, the evidence is consistent with standard models, though the largest structures push against the predicted limits. Future observations with greater precision and wider coverage will help settle the question. But regardless of whether any specific structure breaks theoretical limits, the general picture is clear. The universe contains structure at every scale we have been able to measure. From small galaxy groups to massive clusters to superclusters to great walls, the hierarchy continues without apparent end. This hierarchy is not arbitrary. It reflects the scale invariant nature of the initial density variations. Fluctuations of similar amplitude existed at all scales in the early universe, seeding structures at all scales in the universe we observe today. The scale invariance is itself a remarkable feature, predicted by inflationary models and confirmed by observations. It suggests that the physics of the very early universe had a kind of self-similarity, with the same processes operating at all scales. This self-similarity propagated forward through cosmic history, producing a web with similar patterns at different scales. The filaments connecting galaxy groups look similar to the filaments connecting galaxy clusters, which look similar to the filaments connecting superclusters. The similarity is not exact, but the family resemblance is clear. Understanding this self-similarity has been one of the triumphs of modern cosmology. It connects observations of the present-day universe to theories of its earliest moments, providing a bridge across 14 billion years of cosmic history. The cosmic web is this bridge made manifest. Its patterns encode information about the beginning. Its evolution demonstrates the operation of physical law across cosmic time. Its current state represents the universe as it is now, shaped by everything that came before. Studying the web is therefore a form of archaeology, excavating the past from present observations. The structures we see today are fossils of ancient density variations amplified and elaborated by gravity, but preserving essential information about their origins. This archaeological perspective adds another layer of meaning to our exploration. We are not just cataloging structures. We are reading a record of cosmic history, extracting information about times and conditions utterly different from our own. The biggest galaxy, in this light, is a particular kind of historical document. Its size and properties reflect the conditions at its birth, the density of its natal environment, the mergers it experienced, the gas it accreted. Reading its properties tells us about the past, but the galaxy is just one document among many. The cosmic web contains countless such documents, each with its own story. Together, they form a library of cosmic history, volumes upon volumes waiting to be read. We are only beginning to read this library. Surveys have covered only fractions of the sky to the necessary depths. Analysis techniques are still being developed. Many pages remain unturned. Future research will continue this reading. New telescopes will map larger volumes. New techniques will extract more information from the data. New theories will provide frameworks for interpretation. What will they find? Perhaps they will discover structures larger than any yet known. Perhaps they will find anomalies that challenge current models. Perhaps they will simply fill in details, completing a picture whose outlines are already clear. Whatever they find, the exploration will be worthwhile. Understanding the universe is its own reward, a project that transcends any particular result or conclusion. The cosmic web invites us to understand, and we accept the invitation. Let us continue by examining some of the specific phenomena observed within the cosmic web. These phenomena illuminate the physics of large-scale structure and demonstrate the dynamic nature of the web. One important phenomenon is the interaction between galaxies and their environment. Galaxies do not evolve in isolation. They are influenced by the surrounding gas, the gravitational field of nearby structures, and the flows of matter within the web. When a galaxy enters a dense environment, like a cluster, it experiences several processes that can transform its properties. The hot gas filling the cluster can strip away the galaxy's own gas through a process called ram pressure stripping. As the galaxy moves through the cluster medium, the pressure of the hot gas pushes its cooler gas out, removing the fuel for star formation. Observations have caught this process in action, showing galaxies with tails of stripped gas trailing behind them as they move through clusters. These galaxies are being transformed, transitioning from active star-forming systems to passive ellipticals devoid of gas. The transformation is not instantaneous. It takes hundreds of millions of years or more for a galaxy to be fully stripped. During this time, the galaxy's properties change gradually, its star formation declining as its gas is removed. This environmental transformation explains why galaxies and clusters differ systematically from galaxies in the field. Cluster galaxies tend to be redder, older, and less active. Field galaxies tend to be bluer, younger, and more actively forming stars. The difference reflects the different histories of these galaxies, shaped by their environments. The cosmic web provides the context for these environmental effects. Galaxies fall into clusters along filaments, experiencing the cluster environment for the first time. Their subsequent evolution depends on their trajectory, mass, and initial gas content, as well as the properties of the cluster they enter. By studying galaxies in different environments across the web, astronomers can map how environment shapes galaxy evolution. The results reveal a complex interplay of processes, with multiple factors contributing to the observed diversity of galaxy properties. Another phenomenon worth examining is the growth of galaxy clusters through mergers. Clusters do not form in isolation. They grow by accreting smaller systems, including individual galaxies, galaxy groups, and sometimes other clusters. When clusters merge, the result is a spectacular event that can be detected across the electromagnetic spectrum. The collision of the two clusters' gas components creates shock waves that heat the gas to extreme temperatures. These shocks can be seen in X-ray observations as discontinuities in the gas distribution. The dark matter components of the merging clusters pass through each other with little interaction, since dark matter does not collide in the same way that gas does. This creates a temporary separation between dark matter and gas, with the gas slowed by collisions while the dark matter continues moving. Gravitational lensing observations have captured the separation in several merging clusters. The distribution of mass mapped through lensing differs from the distribution of hot gas mapped through X-rays. The offset provides dramatic evidence for the existence of dark matter, since it cannot be explained by ordinary matter alone. Cluster mergers also provide information about the properties of dark matter. By measuring the offset between gas and dark matter in different mergers, astronomers can constrain how strongly dark matter interacts with itself. So far, the results suggest that dark matter interacts very weakly, consistent with the assumption used in most cosmological models. The merging process takes billions of years to complete. During this time, the clusters gradually coalesce, their gas mixing and their galaxies mingling. The end product is a larger cluster, with properties reflecting the combined masses of its progenitors. This merger-driven growth is one of the primary mechanisms by which clusters gain mass. The most massive clusters have experienced many mergers over their histories, accumulating material from numerous smaller systems. The cosmic web facilitates this growth by channeling material toward cluster nodes. Filaments act as highways, delivering galaxies and gas to the clusters at their intersections. The flow is not constant, but proceeds in bursts as clumps of material fall in from different directions. Observations have traced this inflow in several clusters. Galaxies aligned along filaments are moving toward the cluster center, their velocities indicating ongoing accretion. The filaments are visible as overdensities of galaxies extending outward from the cluster, feeding material into its growing mass. This ongoing accretion connects individual clusters to the larger cosmic web. Clusters are not isolated objects, but nodes in a network, fed by filaments and connected to neighboring structures. Their properties depend not just on their current mass, but on the flow of material through the web. The biggest galaxies within clusters have their own growth stories. They typically sit at cluster centers, where they can accrete material falling in from all directions. Their growth is enhanced by their privileged position, which gives them access to more fuel than galaxies elsewhere. These central galaxies often exhibit signs of recent accretion, including tidal streams from disrupted companions and unusually extended outer envelopes. They are still growing, still adding to their mass through the ongoing infall of material. But this growth eventually slows. As clusters age and their immediate surroundings are depleted, the rate of infall declines. The central galaxy can only grow as fast as material arrives and less material arrives as time goes on. Eventually, the central galaxy reaches a maximum size, determined by the availability of accreting material and the physics of galactic structure. It may be very large by this point, but it cannot grow indefinitely. This limit connects to the broader theme of our exploration. Even the biggest galaxies have limits to their growth. Those limits are set by the cosmic web, by the supply of material flowing along filaments, by the competition with neighboring structures. The web enables growth, but also constrains it. The biggest galaxy is big because the web fed it material. It is not bigger because the web eventually limits the supply. Its size represents a balance between what the web provides and what the galaxy can incorporate. This balance differs for galaxies in different environments. Galaxies at cluster centers have access to the most material, but also experience the most competition. Galaxies in less dense regions have less material available, but face less competition. The resulting range of galaxy sizes reflects these different balances. Understanding these balances requires understanding the cosmic web, the flows of material within it, and the physics that governs how galaxies accrete and grow. The study of galaxy evolution and the study of large-scale structure are thus intimately connected. Another phenomenon that illuminates the cosmic web is the effect of active galactic nuclei, the energetic centers of galaxies powered by accreting supermassive black holes. These nuclei can inject enormous amounts of energy into their surroundings, affecting not just the host galaxy, but the surrounding environment. When matter falls toward a supermassive black hole, it forms an accretion disk that heats to extreme temperatures. Some of this energy is radiated away as light, making the nucleus visible across vast distances. Some is channeled into jets of material that blast outward at nearly the speed of light. These jets can extend far beyond the host galaxy, sometimes reaching millions of light years into intergalactic space. As they propagate, they inflate lobes of hot gas that glow in radio waves. The result is a radio galaxy, a system whose radio emission extends far beyond its optical extent. The largest radio galaxies have lobes spanning millions of light years, dwarfing the optical galaxy at their center. These are among the largest structures produced by individual objects, rivaling small galaxy groups in extent. But even these large radio lobes are small compared to the cosmic web. They represent local perturbations, disturbances created by active nuclei that eventually dissipate into the surrounding medium. The web absorbs this energy, adding it to the overall budget of heat and motion. The jets and lobes also affect their immediate surroundings. They can sweep up gas, creating cavities and shock waves that propagate outward. In galaxy clusters, these cavities are visible in X-ray images as bubbles of relativistic plasma embedded in the hot cluster medium. The energy injected by active nuclei helps regulate the cooling of gas in massive galaxies and clusters. Without this injection, the hot gas would cool rapidly, condensing to form new stars. The jets heat the gas, preventing or slowing this cooling, and thereby suppressing star formation. This feedback process connects the growth of supermassive black holes to the evolution of their host galaxies. It explains why the most massive galaxies stopped forming stars long ago, despite sitting in environments filled with hot gas. The black holes at their centers regulated their growth, preventing further condensation and star formation. The cosmic web is the medium through which this feedback propagates. Energy injected by active nuclei spreads through the surrounding filaments and clusters, affecting gas far from the original source. The web is not passive, but active, responding to and distributing the energy released by the objects within it. This active nature makes the cosmic web even more complex than a static structure would be. The web evolves not just through gravitational dynamics, but through the injection and redistribution of energy by countless sources. Stars, supernovae, active nuclei, and cosmic rays all contribute to this energy budget. Understanding the web requires accounting for all these contributions. Simulations must include not just gravity, but gas dynamics, radiation, magnetic fields, and feedback processes. The computational demands are enormous, but progress is being made. Modern simulations can now reproduce many observed features of the cosmic web, including the distribution of galaxies, the properties of clusters, and the absorption signatures of intergalactic gas. This agreement builds confidence that our physical understanding is essentially correct, but discrepancies remain. Some properties of simulated galaxies do not match observations. Some aspects of intergalactic gas are poorly reproduced. These discrepancies point to gaps in our understanding, areas where the physics included in simulations is incomplete or inaccurate. Resolving these discrepancies is an active area of research. Each improvement brings simulations closer to reality and deepens our understanding of the cosmic web. The ultimate goal is a simulation that reproduces all observed properties, demonstrating that we understand the physics completely. That goal remains distant but approachable. Each generation of simulations reduces the discrepancies. Each new observation provides additional tests. The convergence between simulation and observation is one of the most encouraging trends in modern astrophysics. The cosmic web, in this light, is not just an object of study but a testing ground for physics. By comparing the predicted web to the observed web, we test our theories and identify their limitations. The web reveals our successes and exposes our failures. This testing function gives the study of cosmic structure a unique importance. Many aspects of physics are difficult or impossible to test in laboratory settings. The energies involved are too high, the scales too large, the times too long. But the universe provides natural laboratories where these extremes are realized. The cosmic web is one such laboratory. Within it, physics operates under conditions unavailable on Earth. By observing these conditions, we learn about physics that would otherwise remain inaccessible. The biggest galaxy is part of this laboratory. Its existence tests our understanding of galaxy formation and growth. Its properties constrain the physics of dark matter, gas dynamics, and stellar evolution. Its position in the cosmic web reveals the environmental factors that enable extreme growth. Every galaxy, in fact, is a test of our theories. But the extreme cases, the biggest and brightest and most unusual, provide the most stringent tests. They push theories to their limits, revealing weaknesses that more typical objects might not expose. This is why astronomers study extremes, not just for the wonder they inspire, though that is real, but for the scientific value they provide, the constraints they place on theory, the discoveries they enable. The cosmic web is filled with extremes. The biggest galaxies, the most massive clusters, the emptiest voids, the longest filaments. Each extreme tells us something about the limits of what the universe can produce. And those limits, in turn, tell us about the laws that govern the universe. Physics sets the boundaries. Observations reveal where those boundaries lie. The interplay between physics and observation drives our understanding forward. We have now covered many aspects of the cosmic web and its relationship to large-scale cosmic structure. Let me turn now to some of the implications of this understanding for broader questions about the universe and our place within it. The cosmic web raises profound questions about scale and significance. In a universe organized at every level, from stars to superclusters, what constitutes something important? Are galaxies important because they contain stars and perhaps life? Are clusters important because they are the largest bound structures? Are great walls important because they are the largest coherent patterns? There is no single answer to these questions. Importance depends on context and purpose. For understanding star formation, individual galaxies are the relevant scale. For understanding cosmology, the largest structures provide the best tests. For understanding our own existence, the specific conditions that allowed life to arise matter most. The cosmic web encompasses all these scales and more. It provides a framework within which multiple kinds of importance coexist. Nothing is diminished by the existence of larger structures. Everything retains its significance within its proper context. This pluralistic view of cosmic significance is perhaps the most important lesson of the cosmic web. Size alone does not determine value. The biggest galaxy is not more important than smaller galaxies, just different. Great walls are not more important than superclusters, just larger. Each scale has its own relevance and its own fascinations. For human observers, the relevant scale is personal. We care about our planet, our star, our galaxy, because they are ours. The cosmic web extends vastly beyond anything we will ever directly experience. But it provides the context within which our experience makes sense. Understanding this context enriches our perspective without diminishing our importance. We are small relative to the universe, but size is not the measure of significance. We are significant because we observe, because we understand, because we wonder. These activities require no particular size. The cosmic web, in revealing our context, invites this kind of reflection. It shows us where we are in the grand scheme, not to humble us, but to orient us. We are nodes in a web, connected to vast structures through threads of matter and gravity. We participate in the cosmic order even as we study it. This participation is itself remarkable. Out of all the matter in the universe, a tiny fraction organized itself into structures capable of contemplating the whole. Stars and planets and eventually minds emerged from the same processes that built filaments and voids. We are the universe understanding itself. The cosmic web did not plan this outcome. It operates through blind physical law without intention or purpose. But the outcome occurred nonetheless. Within the web, pockets of complexity arose, including complexity sufficient for reflection. Whether such complexity exists elsewhere in the web is unknown. We have not yet detected intelligence beyond Earth, though we have only begun to look. The universe may be filled with observers, each contemplating their own position in the web. Or we may be alone, the only minds in a cosmos of matter and energy. Either possibility is profound. If we are not alone, the universe is rich with significance beyond our own. If we are alone, then the significance we bring to the universe is unique, a precious rarity in an otherwise unconscious cosmos. The cosmic web does not answer which possibility is true, but it provides the framework within which the question makes sense. Observers, if they exist within the web, at nodes and along filaments, in galaxies scattered through its extent. The web is the habitat of whatever observers exist. This cosmic perspective is both humbling and elevating. Humbling because we are small, elevating because we are part of something vast. The tension between these feelings is not a problem to be solved, but a reality to be embraced. The biggest galaxy exemplifies this tension. It is enormous, far larger than anything we will ever directly experience. Yet it is small compared to the web that contains it. Size is relative. What matters is not where we rank on some scale, but what we do with our position. Understanding is something we can do. We can study the cosmic web, map its structures, probe its physics. We can appreciate its beauty and contemplate its meaning. These activities require no particular size, only the capacity for thought and wonder. The discovery that makes the biggest galaxy look small is therefore not a diminishment, but an expansion. Our horizons have grown. Our understanding has deepened. We see further than we did before, and what we see is magnificent. This is the gift of cosmology, an expanded view of the universe that includes us, but extends far beyond us. The cosmic web is part of this gift, a structure of almost inconceivable scale that nonetheless makes sense to minds on a small planet orbiting an ordinary star. We turn now toward the future of cosmic web research. What questions remain open? What observations might answer them? What discoveries might lie ahead? The cosmic web is still being mapped. Current surveys have covered significant portions of the sky, but not all of it. They have probed to significant depths, but not the deepest possible. Future surveys will extend this coverage, mapping galaxies and structures to greater distances and fainter limits. New telescopes under construction and in planning will greatly enhance our capabilities. Some will operate in optical and infrared wavelengths, detecting the light of distant galaxies. Others will operate in radio wavelengths, tracing hydrogen gas and radio-emitting sources. Still others will detect gravitational waves, ripples in spacetime produced by massive objects and cosmic events. Each new capability will reveal aspects of the cosmic web that were previously hidden. Optical surveys will map galaxy positions with unprecedented precision. Radio surveys will trace the gas flowing along filaments. Gravitational wave observatories may eventually detect the background created by countless sources, providing a new window on large-scale structure. The data from these surveys will be enormous, far exceeding what any human could analyze directly. Machine learning and artificial intelligence will play crucial roles in extracting information, identifying patterns, and testing theories. This computational revolution is already underway. Algorithms can now classify galaxies, measure their properties, and identify their environments more rapidly and consistently than human observers. Future algorithms will be even more capable, handling ever larger datasets with ever greater sophistication. The combination of improved observations and improved analysis will push our understanding forward. Some current uncertainties will be resolved. New questions will emerge. The cycle of observation, analysis, and theory will continue as it has for centuries. What specific discoveries might lie ahead? Predicting scientific discoveries is notoriously difficult, since truly novel findings are by definition unexpected. But some possibilities are worth considering. First, we may discover structures larger than any yet known. Current surveys have found patterns extending across billions of light years, but the observable universe is larger still. Deeper surveys may find coherent structures at even greater scales, pushing against theoretical limits. If such structures are found, they will pose challenges for standard cosmological models. Those models predict limits to structure size based on fundamental physics. Structures exceeding these limits would require explanation, perhaps involving unusual initial conditions, new physics, or modifications to existing theories. Second, we may better understand the nature of dark matter. Current observations constrain its properties, but do not identify its particle composition. Future observations, combined with laboratory experiments, may finally reveal what dark matter is made of. If dark matter is identified, it will represent one of the great discoveries of physics. A new particle or field, invisible to our instruments, yet dominating the mass of the universe, would transform our understanding of nature. The cosmic web, built on dark matter scaffolding, would become a probe of this new physics. Third, we may learn more about dark energy and its role in cosmic evolution. Dark energy drives the acceleration of expansion, determining the long-term fate of the cosmic web. But its nature remains mysterious. Is dark energy constant over time, or does it vary? Is it a property of space itself, or a new field with its own dynamics? Future observations of large-scale structure may help answer these questions, constraining dark energy's properties through its effects on the web. Fourth, we may discover unexpected connections between large-scale structure and other aspects of physics. The cosmic web might prove sensitive to phenomena we have not yet considered, providing new tests of fundamental theories. History suggests that such surprises are likely. Every major advance in observational capability has revealed unexpected features of the universe. The pattern will probably continue. Whatever discoveries lie ahead, the cosmic web will remain central to our understanding of the universe. It is the dominant structure at large scales, the framework within which everything else exists. Understanding the web is essential for understanding the cosmos. This is why the study of large-scale structure attracts so much effort and interest. It is not just one topic among many, but a foundation for all other topics. The insights gained from studying the web inform everything from galaxy evolution to fundamental physics. The biggest galaxy, in this context, is a fascinating special case. It represents the extreme of galactic growth, the outcome of favorable conditions and long evolution. But it is also a window on the cosmic web, revealing how environment shapes galaxy properties and how the web enables and constrains growth. Studying the biggest galaxy is therefore studying the web through one particularly clear example. The lessons learned apply more broadly to all galaxies and all cosmic structures. The specific illuminates the general. This pattern, where specific cases illuminate general principles, is common in science. We study extremes not for their own sake, but for what they teach us about the underlying rules. The biggest galaxy teaches us about growth. The emptiest void teaches us about depletion. The longest filament teaches us about connectivity. Together, these lessons build our understanding of the cosmic web as a whole. We approach the whole through its parts, using specific examples to test and refine general theories. The process is iterative, with observations guiding theory and theory guiding observations. The cosmic web exemplifies this process beautifully. Theoretical predictions, made before the web was fully mapped, have been confirmed by observations. Observations, revealing unexpected features, have prompted theoretical advances. The interplay continues, driving progress on both fronts. This is the nature of scientific inquiry, a conversation between mind and world, with each informing the other. The cosmic web is one participant in this conversation, providing data and challenging theories. We are the other participant, posing questions and interpreting answers. The conversation is far from over. Many questions remain open. Many observations remain to be made. The cosmic web has secrets yet to reveal, patterns yet to be discovered, mysteries yet to be solved. But we have come far. From the first recognition that galaxies cluster together, to the discovery of superclusters and voids, to the mapping of great walls and filaments, our understanding has grown enormously. The cosmic web, once invisible, is now charted across billions of light years. This progress represents one of humanity's great achievements. Without leaving our planet, we have mapped structures spanning the observable universe. Using nothing but light and reason, we have uncovered the organization of the cosmos. This is remarkable by any standard. The discovery that makes the biggest galaxy look small is part of this achievement. It represents a shift in perspective, a recognition that individual galaxies are components of larger structures. This recognition was hard-won, requiring decades of observation and analysis. But it is now established, a foundation for future work. With this foundation in place, the next generation of astronomers will build further. They will map structures we have not yet seen, probe physics we have not yet tested, answer questions we have not yet asked. The cosmic web will be their subject, as it has been ours. And through their work, our understanding will continue to grow. We will see further into the universe and deeper into its nature. We will comprehend more fully the framework within which we exist. This is the endless frontier of cosmology, an ever-expanding understanding of an ever-expanding universe. There is no final answer, no complete understanding, no point at which exploration ends. There is only the ongoing process of discovery, the continuing conversation between mind and cosmos. The cosmic web is the current frontier of this exploration. Beyond it lies the edge of the observable universe, the limit of what light can reveal. Beyond that edge, the universe may extend infinitely, with structures beyond our knowledge and perhaps beyond our comprehension. We cannot see past this edge. We cannot know what lies beyond. But we can study what lies within, mapping and understanding the web that fills observable space. This is enough. This is more than enough. The cosmic web provides endless material for study, endless questions to ask, endless wonders to contemplate. Within its filaments and voids, enough mysteries remain to occupy generations of researchers. And at the nodes of this web, galaxies shine. Some are small and modest. Some are vast and luminous. The biggest among them represents the extreme of what the web can produce through accumulated growth. But even this biggest galaxy is small compared to the web itself. This is not a failing of the galaxy, but a feature of the cosmos. The universe builds at every scale, creating structures without end. No single object can claim supremacy, because each exists within a larger context. Understanding this is the discovery we have been exploring. Understanding this is what makes the biggest galaxy look small and the universe look vast. Understanding this is what transforms our perspective and expands our horizons. The journey through the cosmic web has been long. We have covered much ground, from the definition of the web, to its components, to its evolution, to its implications. But the journey is not over. It continues as long as questions remain and curiosity persists. For now, we pause, but the web remains, stretching across billions of light years, containing trillions of galaxies, evolving slowly through cosmic time. It was here before we noticed it. It will be here long after we are gone. Its existence does not depend on our observation, yet our observation enriches its existence, adding a dimension of meaning that matter alone does not possess. We bring understanding to the cosmos, comprehension of its structures and laws. This understanding is part of reality now, a feature of a universe that includes observers. The cosmic web and its observers form a partnership, each giving meaning to the other. The web provides context for our existence. We provide awareness of the web's existence. Neither is complete without the other. This partnership will continue as long as observers exist and the web persists. Future observers will know things we do not. They will have mapped regions we have not reached, understood physics we have not grasped. But they will share our wonder at the universe's scale and structure. The cosmic web connects us to these future observers through shared subject matter. We study the same structures they will study, ask similar questions they will ask, feel similar awe they will feel. The web is a common heritage, belonging to all observers across time. In this sense, our exploration of the cosmic web is not just a scientific project, but a cultural one. We are building knowledge that will be inherited, developing perspectives that will be refined, asking questions that will eventually be answered. The discovery that makes the biggest galaxy look small is part of this inheritance. Future observers will know it as foundational, a shift in understanding that enabled later progress. They may have better maps and deeper theories, but they will build on what we have learned. This is how knowledge grows. Incrementally, cumulatively, each generation adding to what came before. The cosmic web represents one thread in this growth, a subject that emerged from advances in observation and theory, and will continue to develop through future advances. The biggest galaxy is one point on this thread. Its discovery and characterization represented progress. Its placement within the context of the cosmic web represented further progress. Future discoveries will represent progress still. The thread stretches forward into the unknown, toward discoveries we cannot predict and understanding we cannot imagine. But it also stretches backward, connecting us to all the observers who came before, who first noticed that stars cluster into galaxies and galaxies cluster into groups. We stand on this thread, looking both ways. Behind us lie centuries of progress. Ahead lie possibilities beyond counting. The cosmic web stretches in all directions, larger than we can fully comprehend, but not larger than we can study and appreciate. This is where we find ourselves, small observers in a vast cosmos, understanding enough to be amazed and ignorant enough to be humbled. The discovery that makes the biggest galaxy look small is a reminder of this position. We have learned much. We have much more to learn, and the learning is a joy. Exploring the cosmic web, mapping its structures, probing its physics, is among the most rewarding activities our species has undertaken. It fulfills something deep in us, a drive to understand that defines our nature. The cosmic web rewards this drive with endless material. Every observation reveals new details. Every analysis uncovers new patterns. Every theory tested deepens understanding. The cycle of discovery continues, powered by curiosity and enabled by technology. We are fortunate to live in an era when the cosmic web can be studied in such detail. Earlier generations could only speculate about large-scale structure. Future generations may find the web fragmenting under accelerating expansion. We exist at a moment when the web is fully developed and still accessible to observation. This moment will not last forever. Billions of years from now, the expansion of space will have pulled the web apart, isolating its components into separate cosmic horizons. Observers in that era, if any exist, will see a much simpler universe, lacking the rich structure we can observe. They will not know what they are missing unless records survive from our era to inform them. But we know what they will miss: the glorious complexity of a fully developed cosmic web, with its filaments and voids and clusters and superclusters, stretching across billions of light years. We are the observers who can see this complexity. We are the minds that can comprehend it, at least partially. This is a privilege that entails a responsibility to observe carefully, to understand deeply, to record accurately for those who come after. The study of the cosmic web is part of this responsibility. By mapping structures and developing theories, we create knowledge that can be preserved and transmitted. Future observers, however different from us, may benefit from what we learn. This is a form of cosmic citizenship, participation in an enterprise larger than any individual or generation. The cosmic web connects us not just spatially through shared structure, but temporally through shared inquiry. We are part of a chain of observers extending across time. The biggest galaxy is one object of this inquiry, one focus of attention among many. Its significance lies partly in its properties and partly in what it reveals about the cosmos. It is both an object of study and a window on larger truths. Through this window, we see the cosmic web in all its vastness. We see structures spanning billions of light years. We see matter organized at every scale. We see the framework within which our own existence makes sense. This is the discovery that makes the biggest galaxy look small, not a diminishment, but an enlargement. Not a loss, but a gain. We have expanded our horizons to encompass what the universe has built, and what it has built is magnificent. The cosmic web is one of the great structures of reality, a testament to the organizing power of physical law. Gravity, acting over billions of years, has woven matter into patterns of extraordinary beauty and complexity. We are privileged to observe these patterns. We are fortunate to understand them, even partially, and we are inspired to continue exploring, to push further into the unknown, to learn more about the universe that created us. The journey continues. The cosmic web awaits further exploration. And the biggest galaxy, however impressive, is just the beginning of what there is to discover. Let us now move forward and consider additional aspects of these cosmic structures that further illuminate their nature and the science that reveals them. The measurement of cosmic distances deserves particular attention. Everything we know about the scale of the cosmic web depends on our ability to measure how far away things are. This is not a trivial problem. The universe is vast, and direct measurement is impossible for objects beyond our immediate neighborhood. For nearby objects, parallax provides a distance measure, As Earth orbits the Sun, our perspective on nearby stars shifts slightly. By measuring this shift, astronomers can calculate distances to stars within a few thousand light years. But parallax fails for more distant objects. The shifts become too small to measure, even with the most precise instruments. Other methods must be employed. For more distant stars and nearby galaxies, astronomers use standard candles, objects with known intrinsic brightness. By comparing this known brightness to the observed brightness, distance can be calculated. Dimmer objects are farther away. Certain types of variable stars serve as excellent standard candles. Their pulsation periods correlate with their intrinsic luminosities, allowing distances to be determined from observations of their variations. These stars were crucial for establishing the scale of the local universe, proving that galaxies were external systems rather than nebulae within our own Milky Way. For more distant galaxies, other standard candles are needed. Type Ia supernovae, produced when white dwarf stars explode after accreting material from companions, have remarkably consistent peak brightnesses. Observing these explosions in distant galaxies allows distances to be measured across billions of light years. These supernova measurements revolutionized cosmology in the late 20th century. By observing distant supernovae and measuring their distances, astronomers discovered that the expansion of the universe is accelerating. This discovery, implying the existence of dark energy, won the Nobel Prize and transformed our understanding of cosmic evolution. For the most distant objects, even supernovae become difficult to observe. Here, redshift provides a distance indicator. As space expands, light traveling through it is stretched to longer wavelengths. This stretching, measured as redshift, correlates with distance for uniform expansion. By measuring the redshift of a galaxy's light, astronomers can infer its distance, assuming a model for cosmic expansion. This method has been used to map structures across most of the observable universe, revealing the cosmic web at the largest scales. But redshift distances involve assumptions. They depend on the cosmological model used to interpret them. Different models give different distances for the same redshift. The currently accepted model, based on general relativity and incorporating dark matter and dark energy, provides distances that are consistent with other measurements and produce sensible results. These distance measurements underpin everything we know about cosmic structure: the sizes of great walls, the extents of filaments, the dimensions of voids. All depend on accurate distances. Errors in distance would propagate to errors in structure sizes. Fortunately, multiple distance methods can be cross-checked. Where different methods overlap, they generally agree, building confidence in the distance ladder that connects local measurements to cosmological scales. This consistency is not guaranteed. It required decades of careful work to achieve. Earlier generations of astronomers struggled with systematic errors that produced inconsistent results. Only through painstaking calibration and cross-checking were these errors identified and corrected. The result is a distance scale that is probably accurate to within a few percent for most purposes. This precision allows meaningful statements about the sizes of cosmic structures. When we say that a great wall spans billions of light years, we can be reasonably confident that this is approximately correct. But there is still room for refinement. Current debates about the precise value of the expansion rate suggest that systematic errors may still lurk in the distance ladder. Resolving these debates will require additional observations and analyses. Whatever the outcome, the basic picture of the cosmic web will likely remain intact. The structures are real. Their approximate sizes are known. Details may be revised, but the overall framework will persist. This robustness is important for our confidence in cosmic understanding. We are not building castles on sand, but edifices on solid foundations. The cosmic web exists. Its properties can be measured. Our understanding, while incomplete, is substantially correct. With distances established, the properties of cosmic structures can be studied in detail. Mass is one of the most important properties, determining gravitational influence and dynamical behavior. Masses can be estimated through several methods. For galaxies, rotation curves reveal the gravitational field, which depends on total mass, including dark matter. For clusters, the velocities of member galaxies and the temperature of intra-cluster gas both provide mass estimates. For large-scale structures, gravitational lensing directly maps the distribution of mass regardless of its visibility. These methods have been applied to structures across the cosmic web. Galaxies contain masses ranging from millions to trillions of solar masses. Clusters contain masses ranging from trillions to quadrillions of solar masses. Superclusters contain even more, though their masses are harder to define because their boundaries are less clear. The total mass of the cosmic web is, by definition, the mass of the observable universe. This is dominated by dark matter, with ordinary matter contributing only a small fraction. The observable universe contains roughly 10 trillion kilograms of mass, a number so large that it defies intuition. Within this total, the distribution is highly uneven. Most of the mass is concentrated in filaments and clusters, with voids containing very little. This unevenness is the cosmic web, the pattern of overdensities and underdensities that defines large-scale structure. Understanding how this mass is distributed and how that distribution evolved is central to cosmology. The current distribution reflects the initial conditions plus 14 billion years of gravitational dynamics. By observing the current state and modeling the dynamics, astronomers can infer the initial conditions and test theories of structure formation. This inference is remarkably successful. Models based on inflation and cold dark matter accurately reproduce the observed mass distribution at large scales. The agreement provides strong support for these theories, suggesting that our basic understanding is correct. But discrepancies remain at smaller scales. The predicted number of small dark matter halos exceeds the observed number of dwarf galaxies. The predicted density profiles of halos differ from some observations. These small-scale problems may reflect limitations in our understanding of dark matter or complex astrophysical processes that affect galaxy formation. Resolving these problems is an active area of research. Each possibility has supporters and skeptics. Future observations and simulations will help distinguish between alternatives. Whatever the resolution, the large-scale structure of the cosmic web is well established. The problems arise at smaller scales, where complex physics and observational challenges make the situation less clear. At the scales of great walls and filaments, the theory works remarkably well. This is a testament to the power of physical law. Simple rules applied consistently over cosmic time produce structures of staggering complexity and scale. The cosmic web is not designed or planned. It emerges inevitably from initial conditions and dynamics. This emergence is one of the deep lessons of cosmology. Complex structures can arise from simple rules without guidance or intention. The universe is a vast demonstration of this principle, showing how physical law alone can build a cosmos of breathtaking richness. The biggest galaxy is one product of this emergence. It formed not because any process aimed at producing it, but because conditions happened to allow extreme growth. Other regions produced smaller galaxies or none at all. The variety of outcomes reflects the variety of conditions across the cosmic web. Understanding this variety is part of understanding the web itself. Why do some regions produce massive clusters while others remain nearly empty? Why do some galaxies grow enormous while their neighbors stay small? The answers lie in the details of initial conditions and subsequent evolution. Initial conditions matter because they seed the growth of structure. Regions that started slightly overdense became the sites of future clusters and galaxies. Regions that started slightly underdense became voids. The small differences at the beginning translated into large differences at the end. Subsequent evolution matters because it amplifies these initial differences. Gravity concentrates matter in dense regions, making them denser. Expansion spreads matter in sparse regions, making them sparser. The contrast between overdense and underdense regions grows over time. This growth follows predictable patterns that can be calculated and simulated. The predictions match observations remarkably well, confirming our understanding of the relevant physics. But the initial conditions themselves are not predictable from any deeper theory we possess. They are simply the starting point from which structure grew. Understanding their origin is a frontier of cosmological research. The leading explanation involves quantum fluctuations during inflation, the period of rapid expansion in the earliest moments. During inflation, quantum uncertainties in the inflating field were stretched to cosmic scales, becoming the density variations that seeded structure. If this explanation is correct, then the cosmic web is ultimately rooted in quantum mechanics. The largest structures in the universe trace their origins to the smallest fluctuations imaginable, amplified by cosmic expansion and gravitational dynamics. This connection between quantum and cosmic scales is one of the most remarkable features of our universe. It suggests a deep unity underlying the diversity of phenomena, a common physics linking the subatomic to the cosmological. Testing this connection is difficult because inflation occurred so long ago and at such extreme conditions. But the patterns in the cosmic microwave background and in the cosmic web provide indirect tests so far. The predictions of inflationary models match the observations, supporting the quantum origin of cosmic structure. Future observations may provide more stringent tests. The patterns at the smallest accessible scales, where quantum effects would be most directly imprinted, are the focus of intensive observation and analysis. Whether or not the inflationary picture is confirmed, the cosmic web remains the observed outcome. Its structures exist regardless of their ultimate origin. Understanding that origin would deepen our knowledge but would not change the web itself. The web is the subject of our exploration. Its structures fill the observable universe. Its patterns reveal the physics of cosmic evolution. Its existence provides context for everything within it. The biggest galaxy is a product of this context. It arose from initial conditions that favored its growth and an environment that supplied material for expansion through processes that operated consistently across cosmic time. Its size reflects the web's influence as much as its own properties. This is the perspective that the study of the cosmic web provides. Individual objects are understood through their contexts. Exceptional objects are understood through the exceptional conditions that produce them. Nothing exists in isolation. The isolation we might perceive is illusory. Every galaxy is connected to the web through filaments of matter and gravity. Every cluster is fed by streams of infalling material. Every void is shaped by the structures surrounding it. The web is the connective tissue of the universe, linking all its parts into a coherent whole. Understanding the web is understanding how the parts relate to each other, how local properties reflect global conditions, how individuals fit into the larger pattern. This understanding is still developing. We have mapped the web across billions of light years, but much remains to be explored. We have modeled its physics with considerable success, but refinements continue. We have identified its components and traced its evolution, but new questions keep arising. The exploration continues because the subject is inexhaustible. The cosmic web contains more than any finite study can fully capture. There will always be more to learn, more to discover, more to understand. This is not a frustration, but an invitation. The inexhaustibility of the subject means that exploration can continue indefinitely. There's no danger of running out of questions or discoveries. The web will reward investigation for as long as observers exist to investigate. And the rewards are substantial. Every new observation adds to our knowledge. Every new theory deepens our understanding. The accumulation of insight over time represents genuine progress, a growing comprehension of reality. The discovery that makes the biggest galaxy look small is part of this progress. It represents a step forward in understanding, a refinement of perspective, an expansion of horizons. Future discoveries will bring further progress, further refinements, further expansions. But this particular discovery has a special character. It does not just add facts to our catalog of cosmic objects. It changes how we think about those objects. It reveals that the category of individual galaxies, however impressive its members, is not the ultimate measure of cosmic size. This category shift is more important than any particular measurement. It transforms understanding rather than merely extending it. Such transformations are rare and significant. They mark genuine advances in how we comprehend reality. The cosmic web, revealed through decades of observation and analysis, provides this transformation. It shows us that the universe is organized at scales far beyond individual galaxies. It demonstrates that the biggest galaxy, however enormous, is small within this organization. This is the discovery. This is what reframes our understanding. And this is what invites us to continue exploring, to continue learning, to continue expanding our comprehension to match the universe's vastness. The journey through the cosmic web has brought us far. We have surveyed its structures and components. We have examined its physics and evolution. We have considered its implications and mysteries. But no survey can be complete. No examination can exhaust the subject. The cosmic web extends beyond any single exploration, offering endless depths to those who seek them. This is fitting. The universe should exceed our grasp. It should contain more than we can easily comprehend. The challenge of understanding drives us forward, pushing our capabilities and expanding our horizons. The cosmic web presents this challenge magnificently. It is large enough to humble us, complex enough to challenge us, beautiful enough to inspire us. It rewards study while remaining beyond complete understanding. And within it, galaxies shine, stars form and die, planets orbit and moons circle. And somewhere, perhaps in many places, observers contemplate the web and their place within it. We are among these observers. We have looked outward and seen the cosmic web. We have looked inward and developed understanding. We have shared this understanding with each other, building a collective comprehension that exceeds any individual capacity. This is the human contribution to the cosmos, understanding. We add meaning to a universe that might otherwise lack it. We bring awareness to structures that would otherwise exist unnoticed. We complete, in some sense, what physical law began. The cosmic web does not need us to exist, but we need it to understand. And in understanding, we create something new, a synthesis of observer and observed that is neither alone. This synthesis is the culmination of our exploration, not just facts and theories, but a relationship between mind and cosmos. The cosmic web becomes part of us as we become part of it. Understanding is a form of participation. The discovery that makes the biggest galaxy look small is part of this participation. It is our response to what the universe reveals. It is our adjustment of perspective to match what we observe. It is our growth as comprehending beings. Such growth is perhaps the most important outcome of cosmic exploration. We become larger in mind even as we recognize our smallness in size. We expand in understanding even as the universe expands in space. We participate in something vast through the act of comprehension. The cosmic web invites this participation. Its structures await examination. Its patterns await interpretation. Its existence awaits appreciation. We have responded to this invitation. We have examined and interpreted and appreciated, and we will continue to do so for as long as curiosity drives us and the web remains accessible. This is the open ending of our exploration. Not a conclusion that closes off further inquiry, but an opening that invites continued investigation. The cosmic web stretches before us, vast and intricate and wonderful. And somewhere within it, the biggest galaxy shines, impressive and enormous, yet small within the greater whole. This is the perspective we have achieved. This is the understanding we have developed. This is the discovery that reframes everything. The biggest galaxy is big. The cosmic web is bigger. And our understanding grows to encompass both, expanding with each new observation, deepening with each new insight, reaching toward comprehension of a universe that exceeds imagination but not curiosity. The exploration continues,